Raghu, Rohit, am I audible? Am I audible? Can you hear me? बच्चों, am I audible? Yes, okay. चलो. No. So, everything is clear. Okay. Hi, bachcho. Today we are going to do a 3-hour session. In 3 hours, we are going to focus on electrodynamics. If you ask me which is the most heavyweight in entire physics, heavyweight is electrodynamics. The number of questions coming from here are highest. Most of the questions coming from here are directly formula based. For example, if you look at the last 4-year paper, this single question, that what does the magnetic field due to a current carrying conductor looks like? The same question has been asked multiple number of times. What is the magnetic field inside? What is the magnetic field outside? We will talk about all these things. What I request you is that for the next 3 hours, use your razor sharp focus to mug up every single formula that I write on the board right now. Don't do this that I will do it in the evening, I will do it tomorrow, I will do it day after. Tomorrow never comes, later never comes. So make your spine straight, focus. Whatever we are going to do in the next 3 hours, this is very important. So just focus here and try to mug up everything here and now. Beta, I know that out of all these things, at least 50% of things you already know. The remaining 50% you need to know. And when the question comes on the judgment day, read the question 2 times, 3 times. Once you understand the question, it will click you automatically which particular formula you have to use. Delete, no audio. Audio is there, kids? Can you hear me? Hello? Okay, clear. So what I'm saying, don't waste out on time. Focus here. Okay, everything we do. So let's first start with the electrostatics. Electrostatics is the study of charge at rest, because charge show different property under different type of motion. A charge at rest gives out electric field. A charge which is moving with a constant velocity gives out electric field plus magnetic field. And an accelerating charge particle means when the velocity of the charge particle is not constant. An accelerating charge particle gives out electric field plus magnetic field plus EM wave. Right now we are talking about the charges which are at rest. So we are talking only about the field. Now let's say you have a charge Q1. You have another charge Q2. And both of them are point charges. And the separation between them is R. The force acting between these two charges is directly proportional to the multiplication of the charges. The force acting between these two charges is proportional to 1 upon separation whole square between the two charges. Now better tell me, if the first charge becomes double, the force between the charges becomes double. If the second charge also becomes double, then the first charge becomes double, second charge becomes double. The force acting between the charges becomes 4 times. Notice that the force acting between these two charges is proportional to 1 upon separation between the charges whole square. So if the separation between the charges becomes double, if in place of R you substitute 2R, then after squaring in denominator you will have an extra term of 4. So if the separation between two charges becomes double, the force acting between them becomes 1/4. Similarly, if the separation between the two charges becomes triple, then when the separation becomes 3 times, the denominator becomes 3R square times. 3R square will give you an extra factor of 9 in the denominator. The force will be 19. So when separation becomes double, force becomes 1/4. When the separation becomes triple, force becomes 19. When you have written this, then we add a proportionality constant and we write F equals to K Q1 Q2 upon R square. This K is called Coulomb's constant. The value of K depends upon medium, choice of unit system, both, none. The value of K depends upon medium, choice of unit system, both, none. So the answer to this question is both. People think that the value of K depends only on medium. No, beta. The value of K depends both on medium as well as choice of unit system. For example, somebody might say if K is a constant, how can How can its value depend upon unit system? Remember that you have learned PV equals to nRT. For different choice of unit system, you take different value of R. Means for your SI system, you take R as 8.3, which is 25/3. But when you use the calorie system, you take the value of R as 2. So for different choice of unit system, you take different value of the same constant, right? So the value of K depends upon unit system, material between the two charges, both, none. Answer is both. Better focus here. The value of K in SI unit for vacuum is 9 into 10 raised to the power of 9. Unit betu, value of K, force into R square, Newton meter square per coulomb square, Newton meter square per coulomb square. So in SI system of unit, the value of K is 9 into 10 raised to the power of 9. Easy to remember, 9, 9, 9, 9. Unit, value of K, Newton meter square per coulomb square. Remember that in the CGS system, which is also called Gaussian system, the value of K is 1. Such an easy thing to remember. Gauss was such a smart guy that he took the value of proportionality constant as 1. Easy to remember. So in CGS system, value of K is 1. In SI system, the value of K for vacuum is 9 into 10 raised to the power of 9. For CGS system, Gaussian system, value of K for vacuum is 1. Now, betu, what to do if there is a medium? We say that if there are two charges, point charges Q1 and Q2, separated by distance R, the force acting between them is K Q1 Q2 upon R square. Beta, this K depends upon medium and choice of unit system. For a medium, in place of K, we also write 1 by 4 pi epsilon m. But what is epsilon m? Epsilon m is called permittivity of the medium. Epsilon m is called permittivity of the medium. Now, there is something called relative permittivity. Relative permittivity of a medium is defined as permittivity of medium upon permittivity of free space. Relative permittivity is defined as permittivity of the medium upon permittivity of free space. Easy to remember. You have already learned a quantity called relative density. Relative density is defined as density of medium or density of material upon density of water, right? Similarly, relative permittivity is defined as permittivity of medium upon permittivity of free space. So beta, for a medium, we say that the force acting between two charges is 1 by 4 pi epsilon m Q1 Q2 upon R square. What is epsilon m? Permittivity of the medium. Permittivity of medium can also be written as ER E naught. So the force can also be written as 1 by 4 pi epsilon R epsilon naught Q1 Q2 by R square. Beta, what is epsilon naught? Epsilon naught is permittivity of free space or permittivity of vacuum. Permittivity of free space or permittivity of vacuum when there is no charge anywhere. Now you will say 1 by 4 pi epsilon naught Q1 Q2 upon R square. This is the force acting between two charges separated by distance R in vacuum. So we reach a particular result. We say that the force acting between two charges when kept inside a medium is same as the force acting between two charges when kept in vacuum divided by ER. So force acting between two charges when inside a medium equals to force acting between the same two charges when placed in vacuum divided by ER. So force experienced by a charge when placed inside a medium equals to force experienced by same charge when kept at same separation in vacuum divided by epsilon R. Sorry, not epsilon naught, epsilon R. Epsilon R is called relative permittivity. Relative permittivity. But what is the value of ER? What is the value of ER? Remember that for vacuum, relative permittivity is 1. For vacuum, relative permittivity is 1. For conductors, metals, relative permittivity is infinity. So if you place two charge at certain distance inside a metal, then the force experienced by one of the charge will be 0 because ER is infinity. Next thing, beta, ER and dielectric constant, they are kind of synonyms. So ER or dielectric constant, for which you use bold K, both of them are kind of synonyms. Okay. Now let's move on to the first thing, which is field. If you have a charge Q placed at a place where electric field is E, then the force experienced by this charge Q when placed at a place where electric field is E is given by F equals to QE. But what is F? Sir, F is the force experienced by a charge when the charge is placed at a place where the electric field is E. F equals to QE. F equals to QE. Now your question will be, what is this charge and what is this field? We say that every positive charge creates an electric field in the three-dimensional space around it. Every negative charge also creates an electric field in the three-dimensional space around it. A positive charge creates electric field away from it, while a negative charge creates electric field towards it. A positive charge creates electric field away from it, while a negative charge creates electric field towards it. How do we define electric field at a point in space? So let's say there is a point P in space here. How do we define electric field? What is the strength of electric field here due to all the charge present in the universe? So the standard procedure is to determine the electric field at a point. Place a test charge there. After placing the test charge there, look at the force acting on the test charge. The force acting on the test charge per unit test charge is the field at a point. For example, if I ask you, Bhai Sahab, here at this point in this room, what is the strength of electric field? You will say, sir, let's place a charge here. I will ask you, how much charge do you want to place? You say, okay, sir, let's place a charge of 2 coulomb. Then I ask, how after placing the charge of 2 coulomb, you will define what is the strength of electric field here? You will say, sir, we will look at what is the force experienced by this point charge once it is placed here. Let's say the force experienced by this point charge is 40 Newton. So we will say that the electric field at this point is nothing but force experienced by a charge divided by the magnitude of charge. So 40 by 2. So here the electric field is 20 Newton per coulomb. Look at the unit of the electric field. Unit of electric field is Newton per coulomb. When I say that electric field is 20 Newton per coulomb, it means that if you place a charge of 1 coulomb, it will experience a force of 20 Newton. If you place a charge of 2 coulomb, it will experience a force of 40 Newton. If you place a charge of 3 coulomb, it will experience a force of 60 Newton. 20 Newton per coulomb. So, how to identify what is the strength of electric field at a point? Place a test charge. Look at the force acting on the charge. The force acting on the charge per unit test charge is the field. The force acting on the charge per unit test charge is the field. Sir, what are you saying? I am not able to correlate. Why are you saying these things? Now, listen to this part carefully. This thing is important. Let's say there are 2 charges in space. One charge Q1, and let's say there is a point P in space. Our field theory says that a charge produces electric field in the region around it. So let's say there is a charge Q and there is a point P, and this point P is at a distance R from Q. First thing first, what is the strength of electric field at this point P? So you will say, okay, you wanted to identify what is the strength of electric field at this point P. Place a test charge here. Once you place the test charge here, now look at the force acting on the test charge. The force acting on the test charge per unit test charge is the field. The force acting on the test charge per unit test charge is the field. So the force applied by this capital Q on this test charge will be equals to K Q QT by R square. Hence the field at this point P will be nothing but force acting on the test charge per unit test charge. So you'll write K Q QT by R square divided by test charge. Test charge get cancelled. Hence you can say the electric field produced by a charge Q at a distance R from it is KQ by R square. The electric field produced by a charge Q at a distance R from it is KQ by R square. Beta, if the charge becomes double, then at same point, at same distance, the strength of electric field becomes double. The electric field produced by a charge at a distance r from it is directly proportional to charge. The field produced by a charge at distance r from it is inversely proportional to r square. So if you go at double the distance from charge, the field will become 1/4. If you go at triple the distance from charge, field will become 1/9. Now better focus here. E equals to kq by r. If you have a charge q, then at a distance r from it, the strength of electric field is kq by r square. Electric field is a scalar quantity, vector quantity. Electric field is a scalar quantity, vector quantity. Electric field is a scalar quantity, vector quantity. I wrote here na F equals to QE. Electric field is a vector quantity. Now better focus here. A charge Q at distance r from it produce a field of strength KQ by r square. A positive charge produces field away from it, while a negative charge produces field towards it. So at a distance r from it, if this charge is positive, the field it will produce is away from it. And if this is negative charge, it will produce field towards it. So we have to think, let's say you have a positive charge. Now, at any point in space around it, let's say here, the field produced by this positive charge at this point will be away from it. The field produced by this positive charge at this point will be away from it. The field produced by this positive charge at this point will be away from it. This point away from it. So at all points in the three-dimensional space around a positive charge, the positive charge produces field away from it. To the contrary, in the three-dimensional space around a negative charge, let's say at this point, the negative charge will produce field towards it. At this point, the negative charge will produce field towards it. So at all points in space, a positive charge produces field away from it, a negative charge produces field towards it. What are you trying to explain? Now, connecting all the dots. Let's say, beta, there are two charges Q1 and Q2 in space separated by distance. Q1 doesn't know that Q2 exists in space. Q1 has no idea that there is another charge in the space. A charge Q1 in the three-dimensional space around it creates something called electric field. When the field created by first charge interacts with the second charge experiences a force. How much force? Charge time field at the position of charge. So this charge Q1 creates how much electric field at a distance r from it? So this charge Q1 creates an electric field at position of Q2. How much? KQ1 by r square. And the force experienced by the second charge Q2 is nothing but charge Q2 times field at the position of second charge due to the first charge. Hence you get KQ1 Q2 upon r square as per given by Coulomb's law. Similarly, second charge doesn't know that first charge exists in space. A positive charge simply creates an electric field in the three-dimensional space around it, away from it. A negative charge in the space, three-dimensional around it, creates a field towards it. Q2 doesn't know that Q1 exists. Q1 is at distance r from Q2. At the position of Q1, Q2 will create an electric field KQ2 by r square. If Q2 is positive, it will create field away from it. If Q2 is negative, it will create field towards it. The force experienced by charge Q1 will be nothing but charge times field at position of charge. So charge is Q1 and field at position of charge Q1 due to Q2 is KQ2 by r square. Hence you again get the force experienced by Q1 is KQ1 Q2 by r square. The force experienced by Q2 is also KQ1 Q2 by r square. The force experienced by two charges is equal and opposite in accordance with our Newton's third law. So beta, what am I trying to explain from all this? There is something called field theory. One charge doesn't know that another charge exists in space. A charge creates its own field. When another charge interacts with the field created by first charge, it experiences a force. How much? KQ1 Q2 upon r square. Charge times field produced by other charge at the position of first charge. Let's move on. Now, beta, first thing, how to write field at a point due to multiple charges. So if let's say you have got a charge Q1, a charge Q2 and a charge minus Q3 and you wish to write the field at a point. Write the field due to each individual charge and then add it up. Field is a vector quantity. When you will think of field due to Q1, Q2 and minus Q3, you will get three vectors. Electric field produced by 1, electric field produced by 2, electric field produced by 3. Since field is a vector quantity, when you are adding them, you must do vector addition. Okay. So let's say this positive charge will produce field here away from it. This second positive charge will also produce field away from it. And this negative charge will produce field towards it. Don't add them up just like E1 plus E2 plus E3. Beta, these three are vectors. So you must do vector addition. So let's take one simple example on this. Let's say on the three corners of an equilateral triangle, you have got three identical charges Q, Q and Q. If somebody asks you, what is the net electric field at the centroid of this equilateral triangle? I know that you know that answer is 0. But let's think over it once. You will say that, sir, field is a vector quantity. A positive charge produces field away from it. Due to this charge Q at this point C, due to this charge Q at this point C, you will get a field away from it here. Due to this charge Q at this point C, you will get a field away from it here. Due to this charge Q at this point C, you will again get a field away from it. Field is a vector quantity. When you add up these three vectors of equal magnitude E, and which are equally spaced at angle of 120, 120, 120, then the resultant of these three fields will be 0. Let's do another example. Let's say they give you these four charges, Q, minus Q, minus Q, plus Q. And these four charges are placed at four corners of a square. Now somebody asks you what is the net electric field at center. So beta, tell me what is in which direction this first positive charge Q will produce field at center, away from it, towards it. So sir, this is a positive charge, huh? At that point it will produce field away from it. Let's say the strength of the field produced by charge Q at this distance is E. Let's say this distance, it produces a field E. What will be the direction and magnitude of field produced by the charge Q at same distance from center? So you will say, sir, charge has same magnitude and distance is same. Since the charge has same magnitude as well as distance is same, then the field magnitude will also be same. This charge plus Q will again produce a field away from it, which will be E. So this plus Q produces E, this plus Q produces E. This minus Q will produce a field towards it. And this minus Q will also produce a field towards it, E. Hence, you get 2E here and 2E here. The resultant of this 2E and 2E at angle of 90 degree will be how much? Nahin, not 4 gudda. 2E at angle of 90 degree. Nalaiko. If you have got two vectors of same magnitude R and R inclined at angle theta, then their resultant is exactly midway. And this resultant exactly midway has a magnitude 2r cos theta by 2. If you have got two vectors of same magnitude R and R inclined at angle theta, then their resultant is exactly midway. And this resultant has a magnitude 2r cos theta by 2. If you have got two forces F and F inclined at angle of 60 degree, resultant is 2F cos 60 by 2. What is beta 2F cos 60 by 2? Cos 60 by 2 is cos 30. Cos 30 is root 3 by 2. So you get 2F into root 3 by 2, which is root 3F. If you have got two forces of same magnitude F and F inclined at angle of 90 degree, resultant is how much? 2F cos 90 by 2. Cos 90 by 2, cos 45. Cos 45, 1 by root 2. So 2F into 1 by root 2. What do you get, darling? Root 2F. Okay. Similarly, if you have got two forces F and F of same magnitude acting at angle of 120 degree, resultant is how much? 2F cos 120 by 2. 2F cos 120 by 2. Cos 120 by 2 is cos 60. Cos 60 is half, which is nothing but F. Exactly midway you will get F. Okay, Batu? So this is a small formula, useful one. You must remember this. If you have got right now, if you have got two vectors of magnitude r and r inclined at an angle theta, their resultant is exactly midway. How much? 2r cos theta by 2. If you have got two vectors of same magnitude r and r inclined at angle theta, the resultant is exactly midway. How much? 2r cos theta by 2. So Gutta Kumar, here, what is the resultant of this 2e and 2e? Sir, both have same magnitude. Resultant will be exactly midway. How much? Under root of, 2r. What is one vector's magnitude? 2e cos 90 by 2. Cos 90 by 2, cos 45. Cos 45 is 1 by root 2. So 4e into 1 by root 2. 4e into 1 by root 2 will be 2 root 2e. Okay, beto? Chalo. Now, before we go anywhere, let's talk about null point due to 2-point charges. Null point. Sir, what is null point? Null point is the place where the net electric field is zero. Null point is the place where the net electric field is zero. If you have got two like charges, Q1 and Q2, separated by distance r. Like charges means both are either positive or both are negative. If you have got two like charges separated by distance r, then the null point is found on the line joining the charges, in between the charges, closer to the charge of smaller magnitude. Once more, if you have got two like charges, then the null point is found on the line joining the charges, in between the charges, closer to the charge of smaller magnitude. Here, tell me, which one should I take as bigger? Okay, let's say we say that magnitude of Q1 is more than magnitude of Q2. Now, beta, you will get null point where? On the line joining the charges, in between the charges, closer to the charge of smaller magnitude. I have taken Q2 as of smaller magnitude here. If the charges are in ratio Q1 is to Q2, the distance of null point from the charges are in ratio root Q1 is to root Q2. So if this distance is root Q1x, this distance will be root Q2x. So you will say root Q1x plus root Q2x, closer to the charge of smaller magnitude. Yes. Root Q1x plus root Q2x is r. So your x will comes out to be betu r upon root Q1 plus root Q2. So the distance from Q1 is root Q1 r upon root Q1 plus root Q2. And the distance of null point from Q2 is root Q2 r by root Q1 plus root Q2. So this is something you should know. This is for like charges. Like charges. What if we have unlike charges? What if we have got two charges Q1 and Q2 separated by distance r? One of them is positive, one of them is negative. So again, this time also we get null point on the line joining the charges, outside the charges, closer to the charge of smaller magnitude. On the line joining the charges, outside the charges, closer to the charge of smaller magnitude. Let's say beta, this time the magnitude of Q1 is more than magnitude of Q2. So you will get null point in region 1, 2, 3. So null point is the point at which the net electric field is zero. That point is found on the line joining the charges, outside the charges, closer to the charge of smaller magnitude. Since Q2 is less than Q1, you will get null point somewhere here. Again, betu, if the charges are in ratio Q1 is to Q2, the distance of null point from the charges will be in ratio root Q1 is to root Q2. This time you will say root Q1x minus root Q2x is r. Root Q1x minus root Q2x is r. So x comes out to be r upon root Q1 minus root Q2. So distance from Q1 is Q1 into r upon root Q1 minus root Q2. And here will be root Q2 into r upon root Q1 minus root Q2. One very important thing. We have talked about like charges. We have talked about unlike charges. And believe me, the higher probability is of the third case which I am discussing. If you have got a pair of equal and opposite charge, if you have got a pair of equal and opposite charge, where will you find the null point? If you have a pair of equal and opposite charge, where will you find the null point? Don't say exactly midway. You will get exactly midway when the charges have same sign, exactly midway. Then you will have null point. They will cancel out each other field. If you have a pair of equal and opposite charge, where do you find null point? Answer is no point in space. Due to this charge system, there exists no single point in space where the net electric field will be 0. Hence, this case is studied independently under the heading of dipole. Less magnitude, this is the case of dipole. There is no single point in space at which a dipole doesn't create electric field. So, we have to focus. They will ask you question like this. There is a dipole placed in space and there is a charge placed in space. The charge must experience force, the charge may experience force. The charge must experience force, the charge may experience force. Answer is the charge must experience force. Why? There is no single point in this entire universe where the dipole doesn't create electric field. Since it will create electric field at the position of this charge, hence the charge must experience a force. From Newton's third law, since the dipole will surely apply the force on charge, the charge will surely apply force on dipole. 100% there has to be a net force on this dipole due to charge. Newton's third law. Dipole will apply force on charge surely, hence the charge will apply force on dipole surely. Chalo beta. This was about the null point. Now we will move on how to write field due to multiple different system. Okay, so now if you have got multiple point charges, how do you write electric field at a point P? So write the electric field due to each charge. The electric field produced by a point charge Q at a distance r from it is, the electric field produced by a point charge Q at distance r from it is kq by r square. If the charge is positive, it produces field away from it. If the charge is negative, it produces field towards it. Keep this in mind. So if you have got multiple point charges, how to write the field at a point due to these multiple point charges? So write the electric field due to each point charge and add. Since electric field is a vector quantity, you must do vector addition. Now, electric field due to different type of system, we are going to mug up the formula right now. If you have a circular ring on which the charge is distributed uniformly, everywhere the charge is distributed Q, and this ring has a radius r. What is the electric field at the center of ring? So electric field at the center of a ring is 0. Why 0? So see, charge is distributed over the entire ring. If you think of for one small element, what is the field? If this element has positive charge, then at center it will produce field away from it. For every single charge on the ring, there is a counter charge which will produce field in opposite direction. So these two counter charges, they will cancel out each other field. Similarly, for the frontmost charge, there is a backmost charge. The frontmost charge will produce field towards left, while the backmost charge will produce field away from it towards right. So you can say, sir, electric field is a vector quantity. Yes. Charge is distributed over the ring. Yes. You are asking me what is the field at center. Yes. So as to visualize the field at center due to the ring, I will think of the field at center due to each small charge on the ring. Yes. Each small charge on the ring, if positive, will produce field at center away from them. And you will get here a fan of electric field lines. Now for every single electric field line, there is a counter electric field line and they will cancel out each other field. Hence the net electric field at center will be 0. So the net electric field at the center of a ring is 0. What about axis? If you have a ring with a charge Q and a radius r, then at a distance x on the axis, if the ring has positive charge, beta here I tell every single kid, when you are mugging up a formula, please read the heading carefully. What are we doing here? Sir, electric field. Due to what? A uniformly charged ring. Where? At a point on its axis. If the ring has got positive charge, then at a point on the axis, it will produce field away from it. If the ring has negative charge, then at a point on its axis, it will produce field towards it. At a distance x on the axis, the electric field due to ring will be kqx upon r square plus x square raised to the power of 3 by 2. Use your photographic memory. Mug it up right now. KQX upon R square plus X square raised to the power of 3 by 2. KQX upon R square plus X square raised to the power of 3 by 2. KQX upon R square plus X square raised to the power of 3 by 2. Now, beto, remember the same thing in one more variant. If this is X, this is R. Let's call this distance as R. This distance is small r is under root of R square plus X square. This distance is small r is under root of blah square plus blah square, under root of R square plus X square. So you can even think of it as KQX upon under root of R square plus X square whole cube. So you can even mark this up as KQX by R cube. KQX by R cube, which are the distance of a point on the ring to the point at which you wish to write the field. The distance of a point on the ring from the point at which you wish to write the field. KQX by R cube. You can write it this way also. Now, beta, think, X is there in numerator as well as denominator. As you move from the center of the ring to infinity, X is there in numerator as well as denominator. So as X increases, numerator increases, denominator increases, what happens? So we have to focus here. If you have a ring with a charge Q and a radius R, then if you plot how does the electric field vary with the distance, the electric field strength at center is 0. Sir, electric field strength at center is 0. Yes, now just say it. The electric field due to a ring at its center is 0. And at infinity is 0. At center is 0. Sir, why at infinity 0? At infinity, you are at infinite distance from this charge. The electric field will be 0. Electric field at center of ring is 0. Electric field at infinity is 0. So as you go from center to infinity, electric field strength first increases, then decreases. Electric field strength due to the ring is maximum at a distance x equals to r by root 2. So field due to a ring having a charge q, having a radius r is maximum at a distance on the axis which is same as r by root 2. Better now, I teach this other case as the brother of ring. If you have got two identical charges, which charges? Identical, not dipole, not equal and opposite. If you have got two identical charges separated by a distance d, then what is the electric field at a distance x on their perpendicular bisector? Either they can give you this diagram or they can say that there are two charges q and q separated by distance d. What is the electric field at a point at distance x on their perpendicular bisector? So I am saying this is brother of ring. The formula looks more or less same as that of ring. Okay, so what should I say has to be the formula here? Better focus. For ring, electric field is KQX upon R square plus X square raised to the power of 3 by 2. KQX upon R square plus X square raised to the power of 3 by 2. Take a wild prediction what will be the electric field produced by 2 point charges Q and Q separated by distance d at a distance x on their perpendicular bisector. So you'll say there goes the same type formula. K Q x upon R square plus X square raised to the power of 3 by 2. Beta, what is the charge on whole system here? What is the charge on whole system here? 2Q. The charge on whole system here is 2Q. So K Q x upon, in place of radius, we will substitute by 2 d by 2. So R square plus X square raised to the power of 3 by 2. So KQX upon R square plus X square raised to the power of 3 by 2 works here as well. All you have to remember is, in the case of ring, the total charge on ring was Q. Here, in case of this system, the total charge on system is 2Q. So K 2QX upon R square plus X square raised to the power of 3 by 2. So what is R? R is d by 2. Chalo beto, next thing. Here the electric field is maximum at R by root 2. Here the electric field is maximum at R by root 2. Here electric field will be maximum at what value of X? So sir, here electric field is maximum at, in place of R, d by 2. So you get d by 2 root 2. R by root 2. In place of R, substitute d by 2. That's all. So this case is called brother of ring. Now better focus. If you have a half ring, and let's say this half ring has positive charge. My simple question is, what is the direction of electric field at center? So sir, if the half ring has positive charge, every single element here will produce electric field away from it. Field is a vector quantity. So when I think of resultant of all these vectors, the direction will come out to be downward. Okay. Similarly, if you have a half ring made up of negative charge, then at center, each small negative charge here will produce field towards it. Electric field is vector quantity. When you think of addition of all these vectors, the resultant will be upwards. So if you have got all the positive charge, field will be down. If you have all the negative charge, field will be upward. Now, in the question, they will say, if you have a half ring, having charge per unit length lambda, having a radius r, then what is the electric field at center? You will say that electric field at center is 2k lambda by r. 2k lambda by r. Sorry, capital R. 2k lambda by r. 2k lambda by r. 2k lambda by r. Rato, 2k lambda by r. So if you have a half ring, the electric field due to it at center is 2k lambda. Sir, I am remembering this formula. From where? Sir, same formula. Na? If you have a line charge, if you have a charge distributed over a line, and the charge per unit length is lambda. If you have a line charge and the charge per unit length is lambda, and this is infinitely long, then at a distance r from it, the electric field is also 2k lambda by r. Yes, yes. So if you have got a semicircular loop having charge per unit length lambda, charge is distributed over the length only, then the electric field at center is 2k lambda by r. If you have got an infinitely long line charge, then at distance r from it, electric field is 2k lambda by r. Mug up. Next thing, beta, shell. If you have a shell means empty from inside. Entire charge is present on the surface. If you have a shell with a charge q and a radius r, then remember that field inside the shell due to shell is 0. Field inside the shell due to the charge on shell is 0. Field inside the shell due to the shell is 0. For outside point, you can put the entire charge at center. Field inside the shell due to shell is 0. For outside point, you can put the entire charge at center. So if I think of a point at distance r from center and r is less than radius, field inside the shell due to the shell is 0. For outside point here, put the entire charge at center. For r greater than r, electric field is nothing but kq by r square. Field inside the shell due to shell is 0. For outside point, put the entire charge at center. Field inside the shell due to shell is 0. For outside point, put entire charge at center. If you think of the graph of electric field due to shell versus distance from the center, as you go from center to surface, electric field is 0. Once you reach the surface, just outside surface, electric field is maximum. And as you keep on going away, electric field strength keeps on decreasing. At a point just outside surface, electric field is kq by r square. Repeat after me and focus on this. Field inside the shell due to shell is 0. For outside point, put the entire charge at center and then write the field due to the point charge, which is kq by r square. If that point charge is positive, field will be away from it. If that point charge is negative, field will be towards it. Field due to the shell inside the shell is, sorry. Field due to the shell inside the shell is 0. For outside point, put the entire charge at center. Mug up, important, mug up. Now beta, here 2-3 more points. First, if rather than giving q, they say that this shell has charge per unit area sigma and this shell has a radius r, can you tell me what is the electric field at a point just outside the surface of shell? Sir, what are you saying? The shell has charge per unit surface area sigma and a radius r. What is the electric field at a point just outside the surface of the shell? So you'll say, dekho sir, electric field will be equals to kq by r square. But they haven't given me q in the question. Yes, but they have given you charge per unit area, na, sigma. So you can say that the total charge on the shell is charge per unit area times surface area. Now, if you cancel out this r square with r square, and in place of k, write 1 by 4 pi epsilon naught. So this 4 pi also get cancelled. So remember that electric field at a point just outside the surface of a shell having charge per unit area sigma is sigma by epsilon naught. Field at a point just outside the surface of a shell having charge per unit area sigma is sigma by epsilon naught. Field just outside the surface of a shell having charge per unit area sigma is sigma by epsilon naught. As a matter of fact, this result stands true for any given conductor. If you have any conductor, when you give it charge, the charge get distributed over the surface. Two things here that you must remember. Thing number one, sigma into R is constant. What is the meaning of, sir, sigma into R? R is constant. The local surface charge density times the local radius is constant. So the place where local radius is small, their sigma is more. The place where local radius is big, their sigma is less. So for the surface of conductor, sigma into R is constant. Beta, what is sigma? Local surface charge density. Local surface charge density. What is R? Local radius. Local surface charge density times local radius is constant. This is the first thing. Second thing, if you have a conductor and you give it some charge, all the charge resides on the surface. If at a place on the surface of this conductor, if the local surface charge density is sigma, then the electric field at a point just outside the surface of conductor is nothing but sigma by epsilon naught. So second thing, electric field at a point just outside the surface of conductor at a place where the local surface charge density is sigma by epsilon naught. So beta, see, first we learned what is the field due to a shell. Field due to a shell inside the shell is 0. For outside point, put the entire charge at center. Second point, if rather than talking in terms of Q, they are talking in terms of sigma, then the electric field at a point just outside the surface of shell is sigma by epsilon naught. You must mug up this result, and this thing works for all conductor. If any conductor has at a place local surface charge density sigma, then at a point just outside the surface, electric field is sigma by epsilon naught. Next thing, beta. If you give charge to a solid conductor, if you give some charge to a solid conductor, all the charge given to a solid conductor is found on its surface. All the charge given to a solid conductor is found on its surface. There is no charge in the flesh. So you will say a solid charged conductor is as good as a shell. A solid charged conductor is as good as a shell. So if you have a solid charged conductor, if you have a solid metal sphere, okay, let's say made up of copper, you give it some charge, where will you find the entire charge? On the surface, right? There will be no charge in the bulk, all the charge will be on the surface, just like shell. So a solid charged conductor is as good as a shell. Field inside is 0. For outside point, put the entire charge at center. Next thing, we do. If you have a solid non-conducting uniformly charged sphere, solid non-conducting uniformly charged sphere, solid non-conducting uniformly charged sphere, solid non-conducting uniformly charged sphere. It means that charge is present everywhere, not just on the surface. So remember that as you move from center to surface, electric field strength increases linearly. As you move from center to surface, electric field strength increases linearly. So electric field strength at a distance r, for r less than r, is kq by r square, the value on the surface, into small r by capital R. Kq by r square into small r by capital R. As you go from center to surface, electric field strength increases linearly. At center it is equal to 0. On surface it is kq by r square. Unitary method. At center electric field is 0. On surface kq by r square. So at a distance small r from center, as you go from center to surface, electric field strength increases linearly. For outside point, again put the entire charge at center. To write the field at an outside point, you can directly write field as kq by r square. Field inside a shell due to shell is 0. For outside point, put entire charge at center. When you have a solid non-conducting uniformly charged sphere, as you go from center to surface, field increases linearly. For outside point, put the entire charge at center. So if we draw the graph of E versus R, as you go from center to surface, field increases linearly. Just outside surface, field is kq by r square. For outside point, field is proportional to 1 by r square. Okay, Betu? Let's move on. Now let's move on to something called potential energy. Potential energy. If you have got 2-point charges Q1 and Q2 separated by distance r, then the potential energy associated with system is K Q1 Q2 by R. If you have got 2-point charges Q1 and Q2 separated by distance R, the potential energy associated with the system of these two charges is K Q1 Q2 by R. Betu, tell me, if both the charges are like means both of them are positive or both of them are negative, then potential energy of system will be? If both the charges are like, potential energy of system will be? If both the charges are like, potential energy of system will be positive, negative, 0. So sir, both are like, so either both of them are positive or both of them are negative. So potential energy of system will be positive. If both the charges are like, potential energy of system is positive. For like charges, potential energy is greater than 0. For unlike charges, one of them positive, one of them negative, potential energy of system is less than 0. They might say, oh, stop typing, listen. They might say, for two attracting charges, potential energy is dash, positive, negative, 0. For two attracting charges, sir, if they are attracting, they are unlike charges. If they are unlike charges, potential energy is negative. For two repelling charges, potential energy is positive. For two repelling charges, both of them has to be like, either both of them has to be positive or both of them has to be negative. So if you have got two repelling charges, then the potential energy is positive. If you have attracting charges, then the potential energy is negative. As a rule of convention, when the separation between two charges is infinite, potential energy of system is 0. So when the separation between two charges is infinite, then the potential energy of system is 0. Question is, if separation between two charges is increased, potential energy dash, increases, decreases, remains constant. If separation between two charges is increased, potential energy dash, increases, decreases, remains constant. If the separation between two charges increases, potential energy dash, increases, decreases, remains constant. Answer is may increase or decrease depending upon the nature of charge. But let's say you have got two like charges, positive, Q1 and Q2, both of them are positive. So you will write potential energy as K Q1 Q2 by R. If you have got like charges, potential energy will be positive. As R will increase, denominator will increase, potential energy will decrease. Makes sense. But do realize, if your two charges are negative, means one of them is positive and one of them is negative. Now you will say potential energy is minus K Q1 Q2 by R. As R will increase, the magnitude of potential energy will decrease, but the potential energy is negative. Magnitude will decrease, but it is negative. Negative magnitude decreases. It means that the quantity is increasing. For example, minus 10 to minus 8. Which one has got more magnitude? So minus 10. Which one is bigger, minus 10 or minus 8? So minus 8 is bigger than minus 10. So realize that if you have got unlike charges and R increases, denominator increases, the whole quantity's magnitude will decrease. But since it is negative and the magnitude of negative quantity decreases, it means that the quantity increases. So when separation between two like charges increases, potential energy, when separation between two like charges increases, potential energy decreases. When separation between two unlike charges increases, potential energy increases. Potential energy increases, it becomes less and less negative. Keep this small thing. Next thing, how do you define the electric field at a point? To determine the electric field at a point, bring a test charge from infinity, put at this point. The force acting on the test charge per unit test charge is the field. How do you determine electric potential at a point? Bring a test charge from infinity to this point. The change in potential energy of the system per unit test charge is the potential of this point. Bring a test charge from infinity to this point. The change in potential energy per unit test charge will be the potential of this point. Ek sensor, once more. What? How do you determine field at a point? To determine the field at a point, place a test charge, look at the force acting on the test charge. The force acting on the test charge per unit test charge is the field. Okay. How do you determine electric potential at a point? To determine the electric potential at a point, bring a test charge from infinity to the point. The change in potential energy of system per unit test charge is the potential of the point. So potential of a point is change in potential energy per unit test charge. If you have a charge Q and somebody asks you what is the potential at a point P at distance r from it, you will say, sir, bring a test charge from infinity to this point. When the test charge was at infinity, separation between these two charges is infinite. Potential energies K, Q1, Q2 by infinite, 0. When you bring the test charge to this point, now the separation between these two charges is R. Now the potential energy will be K, Q, Qt by R. The change in potential energy, initially 0, final K, Q, Qt by R. Change in potential energy is nothing but K, Q, Qt by R. So the potential at this point will be change in potential energy per unit test charge. So KQ by R. But how do you determine field at a point? Keep a test charge, look at the force acting on the test charge. The force acting on the test charge per unit test charge is the field at the point. How do you determine potential at a point? Bring a test charge from infinity to the point. The change in potential energy of system per unit test charge is the potential of the point. The potential due to a charge Q at a distance r from it is nothing but KQ by R. The potential due to a charge Q at distance r from it is nothing but KQ by R. So if you have a charge Q at distance r from it, the field due to the charge Q is KQ by R square. If the charge is positive, it produces field away from it. If the charge is negative, it produces field towards it. The potential due to a charge Q at distance r from it is KQ by R. I am openly saying I don't like field that much, but I like potential a lot. Why? I like potential a lot because potential is a dash quantity, scalar vector. Potential is a dash quantity, scalar vector. Abbe potential energy, work, these are scalar quantity. Potential is scalar. Field is vector. It's always easier to play with potential. It's a little more complex to play with field. So it's easier to play with potential. Potential is a scalar quantity. Chalo beta. Remember that a positive charge creates a positive potential in the three-dimensional space around it, while a negative charge will create a negative potential in the three-dimensional space around it. The potential at a point due to a positive charge will be positive, and the potential at a point due to negative charge will be negative. For example, if they say 4 identical charges are placed at 4 corners, not identical, 4 charges are placed at 4 corners of a square of side length A. These 4 charges are Q, 3Q, minus 5Q, 7Q. What is the potential at center? So beta, this Q produces potential at center, away from it, towards it. This Q produces at center potential, away from it, towards it. You will say, sir, what type of stupid question you are asking? Potential is a scalar quantity. It is not away or towards. A positive charge generates positive potential. A negative charge will generate negative potential. That's all. There is no direction association with the potential. Potential is a scalar quantity. So if this distance is how much, by the way? How much? A, root 2A. A, root 2A. So this is root 2A by 2. So root 2A by 2. So that will be A by root 2. At the center, this positive charge will produce positive potential. This positive charge will produce positive potential. This negative charge will produce negative potential. This positive charge will produce positive potential. Abe nahi re, Gagandeep, Bittu. Focus here. So let's say this distance is R. We know that R is nothing but A by root 2. Due to this Q, potential at center, KQ by R. Due to this 3Q, potential at center, K into 3Q by R. Due to this minus, abbe potential is easy. Potential is easy. No headache of, direction. Field is headache. In field, you have to do vector addition. In potential, life is chill. You have to do just scalar addition. So due to Q, KQ by R. Due to 3Q plus 3KQ by R. Due to minus 5Q, minus 5KQ by R. Due to 7Q plus 7 k cube by r. So the net potential at center k cube by r plus k into 3 cube by r minus k into 5 cube by r plus k into 7 cube by r. So k by r can be taken as common. So you can simply write the total charge q plus 3q. 4q minus 5q minus q plus 7q 6q, and in place of r by 2 substitute a by root 2. So here you get a and here you get a root 2 in numerator. That's all. Okay, so which first thing we have learned, if you have a charge q, then at a distance r from it, field is kq by r square, potential is kq by r. Field is kq by r square, potential is kq by r. Now here, field is vector, potential is a scalar. A positive charge produces field away from it, a positive charge produces field away from it, negative charge produces field towards it. A positive charge generates positive potential, a negative charge generates negative potential. Field is vector and potential is scalar. Moving on. Next thing, field potential relationship. Field potential relationship. But a lot of time questions get asked on this. Field potential relationship. This is important. Beto, electric field in x direction is minus del v by del x. Similarly, electric field in y direction is minus del v by del y. Electric field in z direction is minus del v by del z. Do hell with this thing for now. Forget about it. Listen to me carefully what I am saying. If you have a positive charge, if you have a negative charge, what will be the direction of electric field? From positive to negative, from negative to positive. So direction of electric field line will be from positive to negative. Yes. In the vicinity of positive charge, you will have positive potential, negative potential. In the vicinity of positive charge, I will have positive potential. In the vicinity of negative charge, you will have positive potential or negative potential. Sir, at this point, positive charge will produce positive potential, negative charge will produce negative potential. But since this point is closer to negative charge, the net potential at this point will be negative, because here the more dominance will be of negative charge. Why? Because r is less, kq by r. So nearby positive charge, potential is positive. Nearby negative charge, potential is negative. Electric field lines, electrostatic field lines go from higher potential to lower potential to higher potential. Electrostatic field lines are from high potential to low potential. Sir, nahi samajh aaya. Shant. You draw electrostatic field line from positive to negative, negative to positive. Sir, from positive to negative. This is the direction of electrostatic field line. Okay. Nearby positive charge, potential is positive. Nearby negative charge, potential is negative. Electrostatic field lines are from high potential to low potential or low potential to high potential. Sir, electrostatic field lines are from high potential to low potential. Remember that when you move in direction of field, potential decreases. When you move in direction of field, potential decreases. So let's say this figure represents uniform electric field. Think of 2 points A and B. Where is the potential higher, A or B? So when you move in direction of field, potential decreases. Potential at A will be more than potential at B. Now, Bitu, acceleration is the rate of change of velocity with respect to time. Yes. When I say that acceleration is 5 meters per second square, what does it mean? Sir, it means that in every single second, the velocity will change by 5 meters per second. Every single second, velocity will change by 5 meters per second. This is the meaning of acceleration. On the very same line, field is nothing but rate of change of potential with respect to length. Whenever I say that electric field is 4 Newton per coulomb, when I say that field is 4 Newton per coulomb, it means that if you place 1 coulomb charge, it will experience a force of 4 Newton. If you place 2 coulomb charge, it will experience a force of 8 Newton. If you place 3 coulomb charge, it will experience a force of 12 Newton. 4 Newton per coulomb. For every single coulomb of charge, the force will be 4 Newton. Similarly, we can also write another unit of electric field. 4 Newton per coulomb is as good as 4 volt per meter. Look at the unit, 4 volt per meter, 4 volt per meter. It means that for every meter that I move in direction of field, the potential will decrease by 4 volt. 4 volt per meter. For every meter that you move in direction of field, the potential will decrease by 4 volt. So let's say here our electric field is 4 volt per meter. What does it mean? For every single meter you move in direction of field, the potential will decrease by 4 volt. Let's say the potential at A is 50 volt and the distance between A and B is 5 meter. So you will say, when they say that electric field is 4 volt per meter, it means that moving 1 meter in direction of field, potential will decrease by 4 volt. In 1 meter decrease by 4. So in 5 meter decrease by 20. Here potential is 50. After decreasing by 20, here potential will be 30 volt. Sir, I didn't get it. Listen once more. Electric field can be written as 2 units. Let's say strength of electric field is 20. So it can be written as 20 Newton per coulomb or 20 volt per meter. Two ways of thinking on electric field. When I say that electric field is 20 volt per meter, it means that on moving 1 meter in direction of field, potential will decrease by 20 volt. Field potential relationship is very, very important, so focus. Let's say at this point, potential is 100 volt. And there is a point B. And here exists an electric field of 5 Newton per coulomb. 5 Newton per coulomb is as good as 5 volt per meter. So for every 1 meter you travel, potential decreases by 5 volt. Let's say separation between these two is 10 meter. So in 1 meter decreases by 5 volt. In 10 meter decreases by 50. Here 100 decreases by 50. Here will become 50 volt. Here 100 decreases by 50. There will become 50 volt. So this is the idea of field potential relationship. Remember that where is the field potential relationship I wrote? Okay, beta. E equals to minus del V by del X. Electric field in X direction equals to minus del V by del X. Field is nothing but rate of change of potential with respect to length. Field is nothing but rate of change of potential with respect to length. The minus sign here tells us that electric field is from high potential to low potential. 3-4 formula, quickly, then we will move on. If you have a shell with a charge Q and a radius R, we have talked about field already. Field inside the shell due to shell is 0. Outside point, put the entire charge at center. Potential. Beta, if acceleration is dv by dt, if the acceleration of particle is 0, velocity is dash. If acceleration of particle is 0, velocity is dash. If the acceleration is 0, velocity is dash. Constant. If the acceleration is 0, velocity is constant. Similarly, field is nothing but rate of change of potential with respect to length. Field is nothing but rate of change of potential with respect to length. If field is 0, potential is dash. If field is 0, potential is dash. Constant. Remember this. Okay. People say field is 0, so charge is 0, so potential is 0. But field is 0, potential is constant. Acceleration is the rate of change of velocity with respect to time. Field is the rate of change of potential with respect to length. If field is 0, potential is constant. The field inside the shell due to shell is 0. So all the points inside the shell have exactly same potential. All the points inside the shell have exactly same potential. Now, potential is a scalar quantity. You can easily write the potential at the center of shell. Visualize in 3D. If you have a shell with a charge Q, all the charges on the surface, every single small charge on the surface of the shell is at same distance r from center. For one small charge Q1 potential at center will be KQ1 by R, second KQ2 by R, KQ3 by R, KQ4 by R, KQ5 by R. So due to whole charge on shell, potential at center will be KQ by R. Potential at center is KQ by R. Now, since the field inside the shell due to shell is 0, potential of all the points inside the shell is same. Potential is constant. So since the center has potential of KQ by R, all the points inside the shell have same potential. How much? KQ by R. The volume inside the shell is an equipotential volume. Why? Because the field is 0. All the points have same potential. How much? KQ by R. So it up, mug up the statement. Field inside the shell due to shell is 0. Field inside the shell due to shell is 0. Potential inside the shell due to shell is constant. How much? Same at center, same on surface, kq by r. Field inside the shell due to shell is 0. Potential inside the shell due to shell is constant, kq by r. For outside point, field and potential both can be written by putting the charge at center. So field will be kq by r square and potential will be kq by r. I am simply in love with the outside point. Inside point is, sir, for shell field at any point inside the shell is 0. Na? Haan beta, field inside the shell due to shell is 0. Yes. Potential is constant, kq by r. Beta, if acceleration is 0, velocity is constant. Na? Field is nothing but the rate of change of potential with respect to length. If there is no field, all the points will be at same potential. Field inside the shell due to shell is 0. Potential at all points inside the shell is same. Same at center, same on surface, same at all these points. How much? kq by radius of the shell. For outside point, put the entire charge at center for both field as well as potential. If they give you a conductor, a charged conductor, spherical conductor, a charged spherical conductor is same as 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 a shell, because if you have a shell, the charge is entirely present on the surface. If you have a charged spherical conductor, again the entire charge is present on the surface. A charged spherical conductor is same as a shell. Chalo beto, next. If you have got uniformly charged, non-conducting, uniformly charged, non-conducting. Betu dekh, as we go from center to surface, field increases linearly. For outside point, put the entire charge at center. We learned it. Okay, field formula we have learned. As we go from center to surface, electric field is kq by r square into small r by capital R. Beta, no need to mug up the inside point potential formula, but that might be asked in gravitation, not here. Okay, no need to mug up the inside point potential formula. Just remember, potential on the surface of the shell is kq by r, and the potential at center is 1.5 times the potential on surface. Potential at center is 1.5 times the potential on surface. If it is a positively charged sphere, potential at center is 50% more than the potential on surface. So if the potential at surface is 100 volt, potential at center will be 150 volt. If the potential on surface is 200 volt, potential at center will be 300 volt. Okay, beto? So this type of question can be asked. So if you have a solid non-conducting uniformly charged sphere, charge is present everywhere, then the potential on surface kq by r. Potential at center 3 by 2 kq by r. And for outside point life is chill. Electric field is simply kq by r square and potential is kq by r. So sir, what do we have to mug up for solid non-conducting uniformly charged sphere? As you go from center to surface, field increases linearly. kq by r square into small r by capital R. Potential at center is 3 by 2 kq by r. Potential on surface is kq by r. And that's all. Chalo beta, with this thing done, let's move on to capacitor. The first thing, most important thing in capacitor is understanding the basic rule of capacitance. The word capacitor comes from something called capacity. Think that you have got two containers, one with more base area and one with less base area, having same height. Which container you will say has more capacity? You will say that this container 1 has more capacity than the container 2. More capacity means ability to store more. In capacitor, ability to store more what? Ability to store more charge. So the term capacitor comes from capacity, the ability to hold more charge. If you have got any conductors, any goddamn one, if you give it some charge, the surface potential will rise. The more the charge you give, the more the surface potential rises. So the surface potential of the capacitor is directly proportional to the charge given to it. Q directly proportional to P. Every time a physicist sees a proportionality, they add up a proportionality constant and then they write Q equals to CV. The charge given to a capacitor equals to its capacitance times its potential. The easiest one, if you have a shell or a spherical conductor of radius r, what is the capacity of this spherical conductor? So you will say charge given to a conductor equals to its capacity times its surface potential. If you give a charge Q to this spherical conductor, you will say that the surface potential is nothing but KQ by R. And we know that Q equals to capacity times V. Q equals to capacity times V. So rearrange it, you can write Q equals to R by K times V. So this R by K is the capacity. Hence the capacity of this is nothing but 4 pi epsilon naught R. So what is the capacity of a spherical conductor? So nothing, 4 pi epsilon naught R. From where does it come? Q equals to CV. This type of isolated capacitors are of no use in real world. In real world, we use multiple plates capacitor. So the type of one which we use the most is parallel plate capacitor. If you have got two parallel plates, I have drawn two lines, but think of two plates of area A and A. And let's say the separation between these two plates is D. First, I am doing the derivation, so you will have a little bit of clarity over it. If let's say these two plates are connected to a battery of potential V, and some charge goes from here Q, and the same amount of charge leaves from the other plate minus Q. Okay. At a point between the plates, you will get some electric field. If you have got an infinitely large plane sheet, I have drawn a line. Think of an infinitely large plane sheet. If you have got an infinitely large plane sheet having charge per unit area sigma, then if this plane sheet is positively charged, it produces an electric field sigma by 2 epsilon naught away from it. If this infinitely large plane sheet is negatively charged, then it produces an electric field sigma by 2 epsilon naught towards it. So now better here. Here you have got plus Q minus Q, and let's say the plate area is A. Due to the charge plus Q, at this point to the right of it, it will produce field away from it towards right. And at the same point, due to the negatively charged plate, you will get field towards right, towards it. So at this point, the positive plate produces field away from it. The negative plate produces field towards it. The field here at a point will be nothing but field due to positive plate plus field due to negative plate. The field due to positive plate at this point will be nothing but sigma Q by A upon 2 epsilon naught. The field due to negative plate at this point will be again Q by A upon 2 epsilon naught. So why did you write plus? Beta, both the vectors are in same direction. Hence, the net electric field at a point between the plates is Q by epsilon naught A. Q by 2 epsilon naught A plus Q by 2 epsilon naught A. Q by epsilon naught A. Somebody might say, sir, why have you placed the plus charge? So beta, what should I do? I should place minus charge. Then I will get the net electric field between the plates to be 0. Just realize this is the magnitude of field due to the first plate. This is the magnitude of field due to the second plate. Since both of them are producing field in same direction, that's why I have placed the plus charge. This is the net electric field between the plates. Why did I do this particular derivation? Important thing is that they will ask you, in this electric field, what is the contribution of positive plate? What is the contribution of negative plate? So you will say, dekho sir, 50% of this field between the plates of capacitor comes due to positive plate and 50% comes due to negative plate. For example, if you have got these two capacitor plates having charge Q minus Q, let's say at a point in between the plate, electric field is 40 Newton per coulomb. Out of this 40 Newton per coulomb, how much is due to positive plate? How much is due to negative plate? So equal, 20. So you are trying to say, if I remove this negative plate, then the field here will be 20. Yeah, that's what I am trying to say. Okay, that's what I am trying to explain here. So the field between the plates is Q upon epsilon naught A. 50% of it comes from positive plate, 50% of it comes from negative plate. If the electric field between the plates is Q upon epsilon naught A, what is the potential drop across the plate of capacitor? So you'll say there was a potential drop equals to field times distance. And from the basic definition of capacitance, Q equals to C delta V. So rearrange it as Q equals to epsilon naught A by D into delta V. What is this epsilon naught T by D? This is called the capacitance. So capacitance of parallel plate capacitor is epsilon naught A by D. Capacitance of parallel plate capacitor is epsilon naught T by D. But what is A? A is the plate area. What is D? Separation between the plate. If the separation between the plates will decrease, capacitance will increase. If the plate area increases, capacitance will increase. Capacitance of parallel plate capacitor is epsilon naught A by D. Between the plates of capacitor, energy is stored in the form of electric field, magnetic field, both none. So remember that between the plates of capacitor, energy is stored in the form of electric field. Energy stored per unit volume in the form of electric field is given by half epsilon naught E square. Energy stored per unit volume in the form of electric field is given by half epsilon naught E square. So if you have got these two capacitor plates of plate area A having plate separation D, if you have here charge plus Q and minus Q, so you will say energy stored per unit volume. In how much volume energy will be stored? Plate area A times separation between the plates D. Energy stored per unit volume is half epsilon naught, and we have just found electric field in the region between the plates will be Q upon epsilon naught A whole square. So you will say total energy stored is half epsilon naught Q square by epsilon naught square A square into A into D. But I cancel out 1A with 1A and 1 epsilon naught with 1 epsilon naught. So you will say that energy stored between the plates of capacitor is Q square upon 2 epsilon naught A, and in the numerator there is a D. Bring that D from numerator to denominator of denominator, you get Q square by 2C. Sir, why are you doing this particular derivation? You could have directly said, na, energy stored is Q square by 2C. I know that you know. But you should know from where this whole Ramcharitmanas came. It came from the basic definition that between the plates of capacitor, energy is stored in the form of electric field. How much? Half epsilon naught E square. This energy can also be written as half C delta V square. So energy stored can be written as Q square by 2C, can be written as half C into delta V square. Moving on. What is the force between the two plates of a parallel plate capacitor having Q and minus Q? So we say that the force between the plates of parallel plate capacitor is field due to first plate at position of second plate, field due to first plate at position of second plate, multiplied by charge on second plate, field due to first plate at position of second plate, multiplied by charge on second plate. The net electric field between the plates is how much, Betu? Q by epsilon naught A. How do you write the force between the two plates of parallel plate capacitor? Field due to first plate at position of second plate multiplied by charge on second plate. Field due to first plate at position of second plate multiplied by charge on second plate. This is the net electric field between the plates. What is the electric field due to first plate at position of second plate? So sir, the electric field only due to first plate is half of this. So field due to first plate at position of second plate, Q upon 2 epsilon naught A multiplied by charge on second plate. So what do you get, beta? Q square upon 2 epsilon naught A. Okay. So this is the force between the plates of parallel plate capacitor. Notice that this result is independent of D. It depends upon charge on the plate. If the charge on the plate becomes double, capacitance becomes, force becomes 4 times. Q square upon 2 epsilon naught A. If Q becomes double, force will become 4 times. But a world famous question. First of all, when they say isolated charged capacitor, what does it mean? Isolated charged capacitor, what does it mean? When they say isolated charged capacitor, so it means that it is not connected to anything. Isolated charged capacitor. This capacitor is not at all connected to anything. Remember that the charge on an isolated charged capacitor remains constant. The charge on an isolated charged capacitor remains constant. The charge on an isolated charged capacitor remains constant. Important concept. Now, beta, focus. They will say, if you have got isolated charged capacitor and the plate separation is D, If D increases, the force between the plates of capacitor will increase, decrease, remain same. The force between the plates of capacitor will increase, decrease, remain same. The force between the plates of capacitor will increase, decrease, remain same. You'll say, but does this formula contains a D? Plate separation? Nahi na. So you will say no, sir. Independent. So if you have got isolated charge capacitor and you increase the plate separation, then for isolated charge capacitor, the charge on the plate remains constant. If you increase the plate separation, even then the force will remain same. Force is how much? Field produced by first plate at position of second plate, Q upon 2 epsilon naught A. Abey, net field is Q upon epsilon naught A. Due to first at position of second, Q upon 2 epsilon naught A multiplied by charge on second plate Q. So what do you get, Betu? Q square upon 2 epsilon naught A. This is the force formula. Next thing said, if a capacitor is kept connected to a battery and then they do something, they increase D, decrease D. For a capacitor connected to battery, what remains constant? So you will say potential drop across the plate remains constant. Potential drop across the plate remains constant. Now, if they say, listen to me carefully. If keeping the capacitor connected to battery, if the plate separation is increased, what happens to the force between the plates? If keeping the capacitor plates connected with battery, if the plate separation is increased, what happens to the force between the plates? So you will say, dekho sir, capacitance is epsilon naught A by D. In this case, you are keeping potential drop constant. So you will say charge on the plates of capacitor is capacitance times potential drop. Capacitance is epsilon naught A by D into potential drop. If you increase the plate separation, let's say you make the plate separation double. So here capacitance will become half. When you make the plate separation double, D is in denominator, capacitance will become half. If capacitance will become half, from Q equals to C delta V, if capacitance becomes half, it means that the charge becomes half. And if the charge becomes half, then the force between the plates will become 1/4. So beta, please understand that when we say now, force is independent of separation between the plates, given that the charge is not changing. Okay. If charge changes due to the change in plate separation, then the force will change. So now, in this case, potential drop is constant. Two concepts that you have to mug up. Concept number first, isolated, not connected to anything, charge constant. Connected to battery, potential drop constant. Isolated capacitor, charge constant. Connected to battery, potential constant. Next thing we are going to do is we are going to talk about small thing in current electricity. But first of all the basic theory things of current electricity has to be done. You should know that I equals to NEAVD. What is N number of free electrons per unit volume? What is E charge on one electron? What is A, the cross-sectional area? What is VD, the drift velocity? You should know that drift velocity equals to mobility times electric field. You should know that resistance of a wire is rho L by A. You should know that Ohm's law in vector form is J equals to sigma E. All these basic things written in the chapter of current electricity before Ohm's law have to be done very carefully. Every single year, 2 questions are coming from this part only. Current electricity, three questions are coming. Consistently, 2 questions are coming from this bakwas only. For example, when you heat up a material, which is a semiconductor, when you heat up a semiconductor, its conductivity dash increases, decreases. So when you heat up a semiconductor, more and more electrons move from valence band to conduction band. The number of charge carrier increases, its conductivity increases. When you heat up a conductor, then its conductivity decreases, its resistivity increases. Delta R is equals to R alpha R delta T. And all these things are important. So this first part has to be done. So sir, where are we going to focus here? I'm going to focus only on 3 things. First, beta, they will give you a stupid type of thing that, let's say there are 2 resistors connected in parallel. When you have got 2 resistors connected in series, dash is same. When you have got 2 electrical components connected in series, dash is same. Current flowing through them. When you have got two electrical components connected in parallel, dash is same, potential drop across them. So here for both of them, current will be same. So potential drop across first one will be I R1. Potential drop across second one will be I R2. If two electrical components are connected in parallel, then for both of them, dash is same. So you will say, sir, potential drop is same. Potential drop across first one is V, potential drop across second one is V. Current flowing through first one will be potential drop upon resistance, V by R1. Current flowing through second one is potential drop across it upon resistance, V by R2. This is a small thing which people do not use. I don't understand why. Remember that multiple lines connected in parallel to an ideal source are independent of each other. Simple question. In our household, the electrical appliances are connected in series or parallel. In our household, electrical appliances are connected in series or parallel. In our household, electrical appliances are connected in series or parallel. Better focus. Let's say the supply line potential in our house is 220 volts. We have got these multiple devices. Whenever they say TV, fridge, AC, geyser, bulb, just think of a resistor. Let's say this is first device. Let's say this is TV in my house and it has got resistance of 220. And this is the second thing. This is fridge. This has got, let's say, resistance of 55 ohm. And this is AC. It has got of 11 ohm. And this is also geyser. Let's say it has got 22. Question is, Betu, what is the current flowing through the TV? So you'll say, sir, dekho, all the multiple devices are connected in parallel. If you turn off the AC, the current flowing through other do not change. They work as it is. Similarly, if you turn off the TV, the current flowing through other will be as it is. That won't change. Multiple lines connected in parallel to an ideal source are independent of each other. If here potential is X, then all these points will have potential of X plus 220. Current flowing through this will be 220 by 220. How much? Potential drop 220, resistance is 220. How much current will flow? 1 ampere. Current flowing through this will be 220 by 55. 220 by 55 will be 4 ampere. Current flowing through this 220 by 22. 220 by 22, 10 ampere. And current flowing through this 220 by 11, that will be 20 ampere. Now, to focus. If here current is 20, here current is 10, here current has to be how much? KCL. Current coming to the junction is same as current going away from junction. So 10 plus 20, this has to be 30. If here 30, here 4, here current has to be 34. Here 34, here 1, here current has to be 35. Here comes 20, here goes 10. Here current has to be 20, here 20 plus 10, 30, here 30 plus 4, 34, here 34 plus 1, 35. So in our household, multiple appliances are connected in parallel. When appliances are connected in parallel, they are independent of each other. The current which flows through my TV has nothing to do with how much current flows through the AC in my house. Okay? Second thing, power. Power equals to IV. The power dissipated by an electrical component at any instant is same as the current flowing through it in that instance times the potential drop across it at that instant. This works for Zener diode, this works in AC, this works for inductor, capacitor, battery, every place. Power is IV. Power is IV. For a resistor, in place of V, we can write IR. So for a resistor, we can also write I square R. Or for a resistor, we can write IS V by R. So we can even write V square by R. So power equals to IV. I can use everywhere. But power equals to I square R or power equals to V square by R, we can use for a resistor. If you have got two resistors in series, what is same for both of them? Sir, the current flowing through them is same for both of them. If you wish to compare the power dissipated by these two resistors connected in series, which formula will be better for comparison? I square R or V square by R? So, sir, if they are connected in series, to compare the power dissipated, it's better to use I square R. Why? Current is same for both of them in series. So, the one which will have more resistance will definitely dissipate more power. and the one which will have less resistance will definitely dissipate less power. Similarly, if you have got two resistances connected in parallel, R1 and R2, what will be same for these two resistances connected in parallel? Sir, for two resistances connected in parallel, the potential drop across the resistor will be same. Now, to compare the power dissipated by them, it's better to use V square by R. So V is same for both of them. If I tell you R1 is more than R2, first resistance is more than second. So if first resistance is more than second, the power dissipated by first resistance will be less. Better focus. In our household, devices are connected in series or parallel? Devices are connected in series or parallel? Parallel. In our household, which device dissipates more power? AC or LED light? Everybody knows AC dissipates more power, consumes more power. AC has more resistance or LED light has got more resistance. So sir, in parallel, the one which has more power has less resistance. Yes. So remember that AC has got less resistance. LED light has got more resistance. Air condition has less resistance. LED light has more resistance. In which chapter do you study LED? Semiconductors, na? Not an awesome conductor, na? And when you go to buy AC, on the box of AC, it's written 100% copper, means 100% good conductor. Okay, so beta, remember that in our household, devices are connected in parallel. The one which consumes more power is the one of lesser resistance. AC has less resistance than the LED light. This is about power. Let's talk a little bit about battery. If you have a cell of EMFE, two things. If you have an ideal cell bole to no internal resistance. Ideal cell means no internal resistance. If your cell has EMFE, then its positive plate is at a potential E higher than the negative plate. So if the negative plate has a potential X, then the potential of positive plate will be E plus X. So if you have a cell of EMF E, then the positive plate of a cell has EMF E higher than the negative plate. For example, if I tell you this is a 12-volt cell, positive plate has got potential of 50 volt. What is the potential of negative plate? So you will say if the cell has EMF of 10 volt, then its positive plate is at a potential 10 volt higher than the negative plate. So if positive plate has 50 volt, then the negative plate will have 40 volt. Okay, betu? So if you have a cell of EMF 8 volt, what does this mean? It means that the potential of positive plate is 8 volt higher than the negative plate. This is ideal cell. In real world cell, the cell also has got something called internal resistance. What is the name of it? Internal resistance. Internal resistance means resistance due to the chemical inside the cell. Then sir, why do you draw it outside? For the sake of understanding. Do realize this is not my cell. This is not my cell. This whole is my cell. This E and R together are called cell. So EMF is E, internal resistance is R. Beto, let's say you have a cell of EMF 24 volt and you connect it to a resistance of A2. How much current will flow in which sense? Clockwise, anti-clockwise. So you will say, sir, a current of 3 ampere will flow clockwise from the positive plate to the negative plate, right? V equals to IR. So current has to be 24 by 8, 3 ampere clockwise. Now listen to this carefully. Listen, Betu. Current is 3 ampere clockwise. My other question is, this cell is getting charged or discharged? So sir, when do you say that a cell is getting charged? When the current leaves the positive plate of the cell, when the current leaves the positive plate of the cell and enters the negative plate of the cell, you will say that the cell is getting discharged. Normal working. Discharge. When the current leaves the positive plate of cell and enters the negative plate of cell, you will say that the cell is getting discharged. When the current enters the positive plate of cell and leaves the negative plate of cell, you will say that the cell is getting charged. Cell is getting charged. When the cell gets charged, potential drop across the cell is more than the EMF. When the cell gets charged, potential drop across the cell is more than the EMF. Potential drop across the cell is E plus IR. When the cell gets discharged, potential drop across the cell is less than the EMF, E minus IR. So when the cell gets charged, potential drop across the cell is more than the EMF, E plus IR. When the cell gets discharged, potential drop across the cell is less than the EMF, E minus IR. If you have got an ideal cell, then potential drop across the cell is nothing but E. So in real world cell, if they give you question like, there is a cell of EMF 10 volt, somebody measured that the potential drop across this cell is 12 volt. This cell is getting charged or discharged. So you will say, bhai, if the potential drop here is 12, this is getting charged. If the potential drop across the cell is more than the EMF, it is getting charged. If they say that VA minus VB is 8 volt, potential drop across the cell is less than the EMF, then it is getting discharged. Okay, chalo beto. Moving on. Cell ka charge discharge padha diya. Beta, many a times question comes on Wheatstone bridge and meter bridge. Wheatstone beta very, very easy. If you have got these 5 components, electrical component, look at the previous 4-year Odisha paper, here their paper, you will find Wheatstone bridge coming. So what is the condition of Wheatstone? A very useless thing. If R1 by R2 equals to R3 by R4, then the potential of these 2 points is same. This is called the balanced Wheatstone bridge condition. No current will flow through the galvanometer, and this is the condition. So either they can write R1 by R2 equals to R3 by R4, or you can write R1 by R3 equals to R2 by R4, or you can write R1 into R4 equals to R2 into R3. This is the balanced Wheatstone bridge condition. Okay, mark it up. Meter bridge is simply based on Wheatstone bridge, and the length of the wire used is 1 meter. So revise that also. Meter bridge, and revise potentiometer. Potentiometer has been taught in great detail in notes. Please revise potentiometer as well. Question can come from these 2 legs in the instruments also. Chalo beto, let's move on to the next thing. Current, electricity, capacitor ho gaya. Next is magnetism, moving charge and magnetism. Moving charge and magnetism. I tell it to all kids. A lot of your problems will be done given that you focus on the name. Why is the name of this particular topic moving charge and magnetism? All these things are true. When the charge is moving, the charge should first move. A charge at rest creates only electric field. For the charge to create magnetic field, or for the charge to experience force due to the magnetic field, the charge should first move. So moving charge and magnetism. First thing, what is the force experienced by a charge Q going with a velocity V when it is placed at a place where the magnetic field is B? So force experienced by a charge Q when it is moving at a place where the magnetic field is B is given by Q into V cross B. Now kids are a little bit lazy. They don't want to mug up a formula in the way it has been defined. Mug it up this way, Q into V cross B. Nothing like QVB sin theta. No, idiots do it. Smart person. Q into V cross B, Q into V cross B, Q into V cross B. Force acting on a charge, moving with a velocity V at a place where the magnetic field is B, Q into V cross B. Since you are getting the force from the cross product of velocity and magnetic field, you will say that force will be perpendicular to both velocity and magnetic field. Since the force is perpendicular to both velocity and magnetic field, force dot velocity is 0. The dot product of 2 perpendicular vector is 0. Force dot magnetic field is 0. So the force acting on a charge Q moving with a velocity V at a place where the magnetic field is B is given by Q into V cross B. Since you are getting force from the cross product of velocity and magnetic field, force dot velocity will be 0. Force dot magnetic field will be 0. You have to mark this up. Force dot magnetic field is not a physical quantity. Force dot velocity is. Which physical quantity is force dot velocity? So you will say that force dot velocity is power. So now, taking from the top again, the force acting on a charge Q when it moves with a velocity V at a place where the magnetic field is B is given by Q into V cross B. Since force is perpendicular to velocity, force dot velocity will be 0. Force dot velocity represents the power Power provided by a force to the particle. Since F dot V is 0, you can say that the power provided by this force is 0. If the power is 0, it means that work done is 0. Power is the rate of doing work. If the work done is 0, it means that the change in kinetic energy is 0. If the change in kinetic energy is 0, it means that the change in the speed of the charged particle is 0. If the change in speed of the charged particle is 0, it means that the speed of the charged particle can't be changed using magnetic field. Beto, from the top, repeating once more. Focus. Force equals to Q into V cross V. Yes, sir. Force dot velocity is 0. Yes. Hence, the power provided by magnetic force to the charge is 0. Power provided is 0. Work done is 0. Work done is 0. Change in kinetic energy is 0. Change in kinetic energy is 0. Change in speed will be 0. A magnetic force can't change speed of the particle. But magnetic force is a force. Magnetic force provides acceleration. Force provides acceleration. Force by mass is acceleration. Magnetic force do not change the speed, but magnetic force provides acceleration. So magnetic force changes velocity without changing speed. How can you change velocity without changing speed? Magnetic force is a force. The job of force is to accelerate. And if the force accelerates, it means that it will change the velocity. So magnetic force changes velocity without changing the without changing the speed. How does the magnetic force changes the velocity? So answer is magnetic force changes the velocity by changing direction. Remember, we learned that velocity is a vector quantity. To define a vector quantity, you need to define two things: magnitude and direction. There is something called acceleration. Job of acceleration is to change velocity. Acceleration can change the velocity by changing the magnitude, or by changing the direction, or by changing both of them. Acceleration can change velocity by changing the magnitude, or by changing the direction, or by changing both of them. The component of acceleration, or the acceleration responsible for changing the magnitude, is called tangential acceleration. Sir, video not coming. Okay. PK, maybe it's a problem with you. Video is coming, Betu. Other guys, video is coming. Coming. Okay. Bachcho, focus. Focus. Velocity is a vector quantity. To define velocity, we need to define magnitude as well as direction. If the magnitude changes, it means that velocity has changed. If the direction changes, it means that velocity has changed. If any one of them changes, it means that the velocity has changed. The acceleration which is responsible for changing magnitude is called tangential acceleration. The acceleration which is responsible for changing direction is called centripetal acceleration. Magnetic force changes the velocity without changing the magnitude. It means that magnetic force provides centripetal acceleration. Magnetic force provides centripetal acceleration. First thing, projection of charge in transverse magnetic field. Beta, when they say na transverse, orthogonal, normal, take it like 90-degree angle. Hai na? In transverse magnetic field. So let's say you have got this magnetic field into the plane of the paper. Let's say going there. And let's say you have projected a charge Q with a velocity V here. And let's say this charge is positive. In which direction it will experience magnetic force? To know the direction of magnetic force, please use the same method which you have already learned. Do not change the method of direction at this particular junction. Use whatever you have learned, master it once. I'm not at all going to use any method. I will say use the method which you already know. The direction of magnetic force on this positive charge will come out to be upwards. Magnetic force acts towards the center because it provides centripetal acceleration. So center of this circular motion has to be somewhere here. Velocity is here, center of circular motion is here. It will go this type of circular motion. First thing, what will be the radius of this circle? So we have learned that the radius of this circle is mv by qb. You simply get it by equating QVB, magnetic force equals to mv square by r. So radius of circular motion comes out to be mv by qb. This radius of circular motion, which is mv by qb, can also be written as momentum by qb. Magnitude of momentum by qb can also be written as under root of 2m ke by qb, or can also be written as under root of 2mq delta v. This delta v is accelerating potential by qb. So radius of circular motion of charged particle in transverse magnetic field is under root of 2 times mass of the charged particle into charge on the charged particle times the accelerating potential by qb. If in the question they have given projected with same speed, I will use this. Projected with same momentum to compare radius, I will use this. If projected with same kinetic energy to compare radius, I will use it. And if given projected with same accelerating potential, then I will use this guy. The time period of circular motion comes out to be 2 pi m by qb. The important thing you must remember about time period of, sir, tell one time direction. No, Betu, see. At this particular junction, you should, I tell this more different method, more different type of for confusion. Whatever method sir has said, use that same method on its own. Otherwise, it will create a confusion. X person said this, Y person said that, which direction to take. That's why I'm not at all discussing direction. Work on it. Direction is the king in magnetism. Time period will be 2 pi m by qb. Now focus here, Betu. The important thing which get asked here is time period is independent of speed. Time period is independent of speed. So whether the speed is more or less, the time period of charged particle in circular motion is 2 pi m by qb. Cyclotron is based on this particular concept that time period is independent of this speed. Moving on, Betu, one thing which get asked a lot. They will give you radius of circular motion. They will ask you what is the kinetic energy of the charge. Get asked a lot. So Betu, focus here. I am rewriting it. I shouldn't, but I am writing it. You'll write RQB equals to under root of 2m k. The kinetic energy of the charged particle will be square it, both the side equals to r square q square b square by 2m. So take care of it. This question get asked a lot. They will give you magnetic field, radius of circular motion, charge and mass. Then they will ask you what is the kinetic energy associated with the charge, r square q square b square by 2m. When a charged particle is projected such that its velocity is perpendicular to magnetic field, it does circular motion. When charged particle is projected in such a way that its velocity is perpendicular to magnetic field, it does circular motion. What if the charged particle is projected in such a way that its velocity is parallel to magnetic field? So you will say, Dekho sir, the magnetic force acting on a charge when projected in a magnetic field is Q into V cross V. 2-3 small things. If the charge is not at all moving, if the velocity is 0, then what is the force experienced by the charge? So if the charge is not moving, a charge at rest doesn't experience magnetic force. A charge at rest doesn't show any magnetic property. You can even write F equals to QVB sine theta, where theta is the angle between the velocity vector and the magnetic field vector. Now, if the force is parallel to magnetic, if the velocity is parallel to magnetic field, then sine theta will be 0. So if the velocity and magnetic field are parallel or anti-parallel, then the force experienced by charge will be 0. So where to focus? If you have got this uniform magnetic field, okay sir, and in this uniform magnetic field, you have projected a charged particle with velocity in direction of the magnetic field. It won't experience any magnetic force, and hence this charged particle will move in a straight line. So again, when you project the charged particle with a velocity perpendicular to magnetic field, it does circular motion. When you project a charged particle with velocity in direction of magnetic field or opposite to it, it moves in a straight line. Why? Sir, F equals to Q into V cross B, which is QVB sine theta. If the velocity is parallel or anti-parallel, theta is 0 or 180, sine 0 is 0, sine 180 is 0. So if the velocity is parallel or anti-parallel to magnetic field, then there will be no magnetic force experienced by the charge, and the charge will go in a straight line. Marked up. Third case, if your velocity of charge particle is at some angle with the magnetic field, then the charge moves in a helical path. You can break down this velocity into two components. One in direction of field, v cos theta. This component v cos theta is parallel to magnetic field. Due to this component, it moves in a straight line. The other component of velocity v sin theta will be perpendicular to magnetic field. Due to this component v sin theta, it will be doing circular motion. So due to v sin theta, circular motion. Due to v cos theta, straight line. Due to v sin theta, circular motion. Due to v cos theta, straight line. Combination of both look like helical path. In this helical path, two things have to be understood. First, what is the radius of helix? So you will say it does go in circular path due to which component of velocity? V sin theta. In the transverse magnetic field, we know that radius is how much, Betu? mv by qb. In transverse magnetic field, radius is how much? mv by qb. Here the circular path comes due to the velocity v sin theta. So radius of this helix is nothing but mv sin theta by qb. It moves along the field due to the velocity component v cos theta. There is something called pitch. Pitch is the gap between two consecutive turns. It moves a distance along the field due to the component of velocity along the field. How much? V cos theta. From one lowest point to another lowest point, time taken to go is nothing but 2 pi m by qb. So pitch is nothing but velocity in direction of magnetic field time the time between two consecutive turns, which is 2 pi m by qb. Sir, so what do we have to mug up in motion of charge in magnetic field? First thing, force acting on a charge moving in magnetic field B is given by Q into V cross B. Since you are getting force from the cross product of velocity and magnetic field, force is perpendicular to velocity, force is perpendicular to magnetic field, so F dot V is 0, F dot B is 0. Hence the power delivered by the force is 0. Since the power delivered by the force is 0, work done by the force is 0, change in kinetic energy is 0. The magnetic force can't change speed, magnetic force can't change speed, but it's a force, it provides acceleration, it has to change velocity. Magnetic force changes the velocity by changing the direction of motion. Magnetic force provides the centripetal acceleration. If you project a charge particle in a transverse magnetic field, then which type of motion charge particle do? Circular motion. The radius of circle is mv by qb. In place of mv, you can write p. In place of p, you can write under root of 2mke. In place of ke, kinetic energy, you can write charge times accelerating potential q delta v. Next thing, Betu. If the charge particle is projected perpendicular to magnetic field, it does circular motion. If charge particle is projected parallel or anti-parallel to magnetic field, it moves in a straight line. If the charge particle is projected at some angle with the magnetic field, then it goes in helical path. The radius of the helical path from there, mv by qb. Here in place of v, substitute v sin theta. So radius is mv sin theta by qb, and pitch is gap between two consecutive turns. It moves forward due to the velocity v cos theta. It moves forward due to the velocity v cos theta. After reaching one point, completing the turn, time taken will be 2 pi m by qb. So pitch is nothing but v cos theta into 2 pi m by qb. Next thing, force on current carrying wire in magnetic field. Okay, beta. Force equals to Q into V cross B. I know this is a grave injustice, but I am trying to explain. If you divide it with time and multiply it with time, charge flowing per unit time is correct. Velocity into time is length. So remember that there F equals to Q into V cross B. Here F is I into L cross B. There F equals to Q into V cross B. Here F equals to I into L cross B. Remember that if you have got one small section of a current carrying wire of having length vector dl placed at a place where magnetic field is B, then the infinitely small force acting on this infinitely small section will be I into dl cross B. I into dl cross B. df equals to I into dl cross B. df equals to I into dl cross B. Remember to take the direction of dl same as the direction of current. Remember to take the direction of dl same as the direction of current. df equals to I into dl cross b. Now, no, not this. World famous question. If two parallel current carrying wire, okay, no. First, let's talk about one important thing here. If beta your magnetic field is constant, if let's say magnetic field is constant, and if you have a straight wire, okay, then how do you write the force acting on this straight wire? So think of the initial point from where the current starts, think of the final point. Think of this as your length vector, final position vector minus initial position vector. And you will say that the force acting on this current carrying wire will be I into position vector final minus initial cross B. This should be used when the field is uniform, constant everywhere, same in magnitude as well as direction. What to do if you do not have a straight wire? What to do if you have a random shaped wire? Then to, rather than thinking of the whole wire, just think of the first point and last point. Think of a vector from the first point to the last point and use it as L effective vector, just like displacement vector from initial to final. Then you will say that the force acting on this current carrying wire is nothing but I into L effective cross B. I into L effective cross B. The most important thing which get asked here is this. If let's say you have got this semicircular loop carrying a current I placed in a magnetic field B, and let's say the semicircular loop has a radius R. Question is, what is the magnetic force acting on this semicircular loop? So you will say, I won't think of the semicircular loop. I will just think of the first point and last point. So the effective length, just like displacement, will be 2R. So the force will be equals to I into L effective cross B. Now use the same direction method which has been already taught to you. Here the force will come out to be L cross B upwards. So force equals to I into L effective, which is 2R, into magnitude of magnetic field B, and which is sine 90. Angle between length vector and magnetic field is 90 degrees, so sine 90. So you get I into 2R into B. Beta, sachi. I am teaching all this to reach a point which I know is important and from where question comes. What is the net force acting on a current carrying loop placed in uniform magnetic field? What is the net force acting on a current carrying loop placed in uniform magnetic field? So if you have a current carrying loop, whole closed loop, and this is placed in any uniform magnetic field, you will say that the net force acting on a current carrying loop placed in uniform magnetic field is 0. The net force acting on a current carrying loop placed in uniform magnetic field is 0. Why? So देखो, force equals to I into L effective cross B. Yes. How to find L effective? Just like displacement. If you have a closed current carrying loop, then the overall displacement is 0. If the overall displacement is 0, it means that the net force acting on it is 0. The net force acting on a current carrying loop placed in a uniform magnetic field is 0. Keep this small thing in mind. Chalo bachcho, let's move on. Focus here. Before I go, length effective is 0. The net force acting on a current carrying loop placed in uniform magnetic field is 0. Now focus beto. Let's think that you have got this current carrying loop, carrying current this way. And let's say here magnetic field is towards right. Okay. My first question, what is the net force on this current carrying loop? So you'll say the net force on this current carrying loop placed in a uniform magnetic field has to be 0. Okay. This triangle has got 3 sides. Let's call the 3 sides 1, 2, 3. My next question, the net force on the whole loop is 0. The net force on one of the side is also 0. On which side there is no force due to the magnetic field? On which side out of 1, 2, 3 there is no force? The net force on the whole loop is 0. No doubt on that. I am saying on one of these three side, on one of the side force is 0. Which side will be that? Side number 3. Why, sir? Arey sir, yaar, force equals to I into L effective cross B. If the angle between L effective is 0 or 180, then the force experienced by that side will be 0. Since this side has got current anti-parallel to magnetic field, it means that the force experienced by 3 will be 0. So remember that the force experienced by 1 and 2 have to be equal and opposite. क्या बोल दिया आपने? Listen. Force experienced by 3 side, net force acting on the current carrying loop placed in uniform magnetic field is 0. Net force acting on the current carrying loop placed in uniform magnetic field is 0. These two experience force, 1 and 2 experience force. Net force on all the 3 side combined is 0. Yes. Force on third side is 0. Yes. Net force on the whole loop is 0. Force on third side is 0. It means that the force acting on 1 and 2 are equal and opposite. The force acting on 1 and the force acting on 2. These two vectors are equal and opposite. Okay? Keep it in mind. Chalo beto, moving on. Let's quickly talk about electric dipole and electric dipole in uniform electric field. What is electric dipole, sir? A pair of equal and opposite charge separated by some distances. Electric dipole. How do you write electric dipole moment? Electric dipole moment is defined as charge times the position vector of positive charge with respect to negative charge. But what is Q? Charge. What is R? Position vector of positive charge. Position vector of positive charge with respect to negative charge. Position vector of positive charge with respect to negative charge. I will come back to moving charge and magnetism. I have to cover few points here. Now beta, if you have a short dipole, 3-4 things. Thing number 1, at a point on its axis, the direction of electric field produced by the short dipole is same as the direction of dipole moment. So at a point on the axis of dipole, direction of electric field created by dipole has the same direction as that of dipole moment. So if you have a dipole at a point on its axis, the direction of electric field is same as that of dipole moment. How much is the electric field? 2 kp by r cube. For a short dipole, I am saying. At a point on the equatorial line, a dipole produces electric field in direction opposite to the dipole moment. How much electric field? Magnitude wise, half of it. So there 2 kp by r cube. Here strength of electric field is kp by r cube. And direction opposite to the dipole moment. Most important thing I am saying. So if there is a dipole, then at a point on its axis, the direction of electric field is same as that of dipole moment, 2 kp by r cube. At a point on equatorial line, direction of electric field is opposite to dipole moment. How much? Kp by r cube. Next thing, potential due to a dipole. If you have a dipole of dipole moment P, and you wish to write the potential due to this dipole at a point in space whose position vector with respect to center of dipole is r and this angle is theta. So remember that the potential at this point due to the dipole is given by Kp cos theta by r square. Maga formula Kp cos theta by r square. Kp cos theta by r square. Sir, first of all, first thing to maga. What is dipole moment? Dipole moment is charge times position vector of positive charge with respect to negative charge. Dipole moment is charge times position vector of positive charge with respect to negative charge. Due to a dipole, electric field at a point on the axis has the same direction as that of dipole moment. How much? 2 kp by r cube. Due to a dipole, the electric field on the equatorial line has the opposite direction. How much? Kp by r cube. Next thing, the potential due to a dipole at a point in space. Potential due to a dipole at a point in space is given by Kp cos theta by r square. 2 years back came in NEET. Kp cos theta by r square. You should have no doubt in the formula. You shouldn't be like on judgment day. Is there a 2 here? Nah. Is there a 2 here? Nah. It's r cube? Nah. It's r square? Nah. You must be sure about the formula. Kp cos theta by r square. This is the potential due to dipole at a point in space. Now the next heading, where you have to mug up 4-5 points. What will happen if you place a dipole in uniform electric field? So when you place a dipole in uniform electric field, irrespective of orientation of dipole, force experienced by dipole in uniform electric field is 0, irrespective of orientation of dipole. Force experienced by dipole in uniform electric field is 0. Second point, torque experienced by dipole in uniform electric field is P cross E. Force experience is 0. Torque experience is P cross E. P cross E can be also written as PE sin theta. Torque experienced by the dipole in uniform electric field will be 0 when when theta is 0 or when theta is 180. Torque experienced by dipole is P sin theta. So torque experience will be 0 when theta is 0 or theta is 180. Third, hence theta equals to 0 degree and theta equals to 180 degree are the orientation of equilibrium. For all position force is 0. Torque is 0 when theta is 0 or when theta is 180. So when theta is 0 or when theta is 180, torque acting on the dipole is 0. So these two are position of equilibrium. Beta, remember that theta equals to 0 is the position of stable equilibrium. Theta equals to 180 is the position of unstable equilibrium. Last thing, the potential energy of dipole in uniform electric field is minus P dot E, which is same as minus PE cos theta. Potential energy is minus P dot E, which is same as minus PE cos theta. For which orientation potential energy is minimum? At the orientation of stable equilibrium, potential energy is minimum. So potential energy minimum at theta equals to 0 degree. How much? Minus PE cos 0. Cos 0 is 1. So potential energy minimum at theta equals to 0 degree minus PE. At orientation of unstable equilibrium, potential energy is maximum. So potential energy maximum at theta equals to 180 degree. How much? Plus PE. Better focus. The heading going on is electric dipole in uniform electric field. If you place an electric dipole in uniform electric field, irrespective of orientation of dipole, the force experienced by dipole will be 0. The force experienced by dipole will be 0. Torque experienced by dipole is P cross E. Torque is P cross E. Force is 0. Since torque is P cross E, it can also be written as PE sin theta. So torque will be 0 when theta is 0, sin 0 is 0, or when theta is 180, because sin 180 is also 0. For theta equals to 0, you will say stable equilibrium. For theta equals to 180, you will say unstable equilibrium. Potential energy is given as minus P dot E. For stable equilibrium, potential energy is minimum. For unstable equilibrium, potential energy is maximum. Keep these things in mind. Sir, why did you jump suddenly to dipole from magnetism? Because of this. If you have a current carrying loop placed in a uniform magnetic field, then the net force acting on the current carrying loop placed in a uniform magnetic field is 0. A current carrying loop is a magnetic dipole. 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 Just the way we define electric dipole moment as charge times position vector of positive charge with respect to negative charge. For a current carrying loop, we don't define magnetic moment same way. We say that the current magnetic moment associated with a current carrying loop is nothing but number of turns in the loop times the current flowing in the loop times the area vector of the loop. Magnetic moment is given by NIA, number of turns in the loop times current in the loop times the area vector of the loop. If in the loop current is clockwise, you say magnetic moment is inward. If in the loop current is anti-clockwise, use the knock-knock rule, curl the fingers of right hand in the sense of current. You will say magnetic moment is outward. So if current is clockwise, what is the direction of magnetic moment? Inwards. If current is outwards, what is the direction of magnetic moment? Outwards. Beta, same things work here also. If you have got this uniform magnetic field rather than electric field, and you have suspended here a current carrying loop. A current carrying loop is nothing but a magnetic dipole. First point, irrespective of orientation of this current carrying loop, the force experienced by this current carrying loop will be 0. Second, the torque experienced by this current carrying loop will be M cross B. Beta, what is M? M is magnetic moment. Magnetic moment of a current carrying loop is nothing but number of turns into current into area vector. Torque will be 0. When magnetic moment is parallel or anti-parallel to magnetic field. Torque will be 0 when magnetic moment is parallel or anti-parallel to magnetic field. Where to focus? You have got 3 circular loops carrying clockwise current. The first circular loop carrying clockwise current is placed in a magnetic field into the plane. The second circular loop carrying clockwise current is placed in a magnetic field coming out of the plane. And the third circular loop carrying clockwise current is placed in a magnetic field towards right. Question is, the first loop experiences a torque, yes or no? And if no, then it is in stable equilibrium, unstable equilibrium. So you will say, Dekho sir, do hell with the loop shoe. Let's focus on magnetic moment. What is the direction of magnetic moment of this loop? Into the plane. So you will say, since the angle between M is parallel to magnetic field, theta is 0, torque is 0, and since theta is 0, you will say this is stable equilibrium. Torque is 0. But to tell me here, what is the angle between magnetic moment and magnetic field? So you will say, Dekho sir, current is clockwise. Curl the finger of right hand. The direction of thumb gives you the direction of magnetic moment, that is into the plane. So the angle between magnetic moment and magnetic field is 180 degree. So you will say, Dekho sir, here magnetic moment is anti-parallel to magnetic field. So theta is 180 degree. This is unstable equilibrium. Okay. Here, Betu, what is the potential energy in this case, third case? Magnetic field is in the plane of the loop. So you will say, Dekho sir, pakao mat. Magnetic moment inward, magnetic field in the plane. Angle between magnetic moment and magnetic field is 90. So now torque will be maximum. How much? MB and IAB. Because sin 90 will become bulk. And potential energy, which is minus MB cos theta, will become 0. Okay, because theta is 90 degree. So first thing, force is 0. Second thing, torque is M cross B. Third thing, theta equals to 0 degree and theta equals to 180 degree are the positions of stable and unstable equilibrium. And fourth point, potential energy is again given by minus M dot B. Do understand here, theta is angle between what and what? Theta is angle between what and what? Theta is angle between what and what? 90% of time you will do this question wrong because you won't understand theta is the angle between what and what. Theta is the angle between magnetic moment and magnetic field. Theta is the angle between magnetic moment and magnetic field. For example, in question, they will say, there is a circular coil carrying current. The magnetic field makes an angle of 30 degree with the plane of the circular coil. How much torque act? So you will say, Dekh bhai, Pagamat, torque formula is easy. Torque is given by M cross B, and we know that M is nothing but NIA. So NIA cross B. So that will be nothing but NIAB sin theta. Fair enough. But what is theta here? Angle between magnetic moment and magnetic field. Now, if the current is this way, okay, let's say I make this side dotted, so you will understand. Both side is towards you, dotted side is behind. Okay, current is going this way. If the current is going this way, what is the direction of magnetic moment, Betu? Up. If the current is going this way, curl the fingers of right hand in the sense of current. Direction of magnetic moment up. So the angle between magnetic moment vector and magnetic field vector is 60 degree. So Betu, just focus. Torque acting on magnetic dipole is M cross B. Here M is here theta is the angle between magnetic moment and magnetic field. Many a times students do this question wrong because they just can't see what is the angle to be taken. Chalo Betu. Next thing, what is the magnetic field due to a circular loop? What is the magnetic field due to a current carrying wire? Biot-Savart's law. Biot-Savart's law says that if you have a current carrying wire, it produces a magnetic field. The magnetic field produced by a small element dl of a current carrying wire at a point in space whose position vector is r is given dB equals to mu naught by 4 pi I dl cross r by r cube. dB equals to mu naught by 4 pi I dl cross r by r cube. dB equals to mu naught by 4 pi I dl cross r by r cube. Beta, the value of mu naught by 4 pi is 10 raised to the power of minus 7. dB equals to mu naught by 4 pi I dl cross r by r cube. In last test, a question came. A small current element is placed here. The length was given, I think, 0.05 meter. And a current of 10 ampere is flowing here. What is the magnetic field at a distance of 1 meter here? I think this was the question. So it is simply mu naught by 4 pi, 10 raised to the power of minus 7. I, 10, dl cross r. Angle between this dl length vector and r vector is 90 degree. So dl cross r, dl into r, 1 into sine 90 divided by r cube. So maga the formula, mu naught by 4 pi I dl cross r by r cube, mu naught by 4 pi I dl cross r by r cube, mu naught by 4 pi I dl cross r by r cube, mu naught by 4 pi I dl cross r by r cube. What is the magnetic field due to a circular current carrying loop, carrying a current I, having a radius r at its center? You will say that magnetic field at the center of a current carrying loop, carrying a current I, having a radius r is given by mu naught I by 2r, mu naught I by 2r, mu naught I by 2r, Rado, mu naught I by 2r. If this has single turn, then mu naught I by 2r. If you have got n number of turns, then the magnetic field becomes n mu naught I by 2r. Better focus. Yesterday's paper question. If there is a charge q going with a velocity v in a circle of radius r, then what is the magnetic field produced at center due to the circular motion of this charge? So you'll say, dekho sir, when you have a circular current carrying loop, carrying a current I, then the magnetic field at center is mu naught I by 2r. Repeat after me, mu naught I by 2r. Now, if you have a charge q going with a velocity v, then the current associated with the motion of this charge will be q upon time taken to complete one circle, 2 pi r by v. Now the magnetic field produced at center due to motion of this charge will be mu naught qv upon 2 pi r. In place of I have substituted, divided by 2r. So what you get is mu naught qv by 4 pi r square. This is the magnetic field, mu naught qv by 4 pi r square. Next thing, betu. If you have a circular current carrying loop, then how to write the magnetic field at a distance x on its axis? Then how to write the magnetic field at a distance x on its axis? This formula is a little bit tricky. Beto, focus. Due to a circular loop at center, beto, how much? Mu naught I by 2r. At a point on the axis, mu naught I r square by 2 times of r square plus x square raised to the power of 3 by 2. So what are we mugging up? There is a circular loop. Raghuvamshi is asking, r equals to mv by qv won't work here. Gudda Kumar, that's why I say Betu, when you are reading something, read the heading first. What is r equals to mv by qb? What is r? The radius of circular motion when a charged particle is projected in transverse magnetic field. Okay. Here, beta, this is the magnetic field produced due to the circular motion of a charge at its center. Kya bol rahe ho, sir? The r equals to mv by qb is the radius of circular motion when a charged particle is projected in transverse magnetic field. That is different. Here, b is the magnetic field produced at the center due to the circular motion of charged particle. Both are different things. Okay. Here, motion of charge is producing magnetic field. Their charge is doing circular motion in somebody else's magnetic field. Both are in different cases. Get it back. What are we mugging up? If there is a current carrying circular loop of radius r carrying current I, then what is the strength of magnetic field at a point on its axis? How much, Beto? Mu naught I r square upon 2 times of r square plus x square raised to the power of 3 by 2. Maga, mu naught I r square upon 2 times r square plus x square raised to the power of 3 by 2. Chalo, Beto. If you have got a finite current carrying wire carrying current I, then what is the magnetic field due to this finite current carrying wire at a distance r from it? You will say, dekho sir, easy. Join the two extreme. Let's say this angle is theta 1 and theta 2. The magnetic field at this point comes out to be mu naught I by 4 pi r sin theta 1 plus sin theta 2. Mu naught I by 4 pi r sin theta 1 plus sin theta 2. Mu naught I by 4 pi r sin theta 1 plus sin theta 2. Mu naught I by 4 pi r sin theta 1 plus sin theta 2. What are we learning? Magnetic field at a point due to a finite current carrying wire. Step 1, drop the perpendicular. Find the shortest distance. Step 2, join the two extremes. Find the angles with the shortest distance line, and then use the formula. Magnetic field is mu naught I by 4 pi r sin theta 1 plus sin theta 2. Mu naught I by 4 pi r sin theta 1 plus sin theta 2. Mu naught I by 4 pi r sin theta 1 plus sin theta 2. Next thing, beta. If your wire is infinitely long, then theta 1 becomes 90 degree, theta 2 becomes 90 degree, then the magnetic field comes out to be mu naught I by, let's say at a point at distance r, mu naught I by 4 pi r sin 90 plus sin 90. Sin 90 is okti, sin 90 is okti plus okti, rendu. So you get mu naught I by 4 pi r into 2. So that is mu naught I by 2 pi r. So if you have an infinitely long wire, then the magnetic field produced by this infinitely long wire at a distance r from it is mu naught I by 2 pi r, mu naught I by 2 pi r. If you have a semi-infinitely long wire, infinite on one side but not infinite on other side, then the magnetic field at a point at distance r, for this case, you will take theta 1 as 0. Drop the perpendicular. When you join the first extreme, you get 0. When you join the other extreme, you get 90 degree. Now the magnetic field will come out to be mu naught I by 4 pi r sin 0 plus sin 90. So beta sin 0 is 0, sin 90 is 1. So what you get is mu naught I by 4 pi r. Now, we have talked about circular loop, we have talked about straight wire. Their combination question can be asked. At least practice out 10 questions, any 10 questions on their combination from the material, at least 10 questions. As a matter of fact, from here till your NEET, 5 questions will come in grand test only. At least do those 5 questions carefully. You guys are not listening to paper discussions carefully. Please enhance it. Write paper attentively and listen to paper discussion carefully. It will help you in growing slowly. Chalo betu, next thing. If you have a solenoid of finite length, having n as the number of turns per unit length. What is n, betu? Number of turns per unit length. When you drive some current I in this solenoid, what is the magnetic field at a point P inside it? So beta, simple. Drop a perpendicular, join the two extremes. Let's say the angle is theta 1 and theta 2. So you say that the magnetic field at a point inside this solenoid of finite length is mu naught Ni by 2 into sin theta 1 plus sin theta 2. Mu naught Ni by 2 into sin theta 1 plus sin theta 2. Mu naught Ni by 2 into sin theta 1 plus sin theta 2. Sir, haven't got it. Listen. Let's say you have got a solenoid of finite length. This whole bakwas which I say now before writing the formula, that is also equally important. If you have a solenoid of finite length, having number of turns n, having a length L. So having number of turns per unit length n by L. Now if you wish to write the magnetic field at a point inside this particular solenoid, step 1, drop the perpendicular, join the two extremes. Let's say the two angles on joining the two extremes is theta 1 and theta 2. The magnetic field at this point is mu naught Ni by 2 into sin theta 1 plus sin theta 2. Mu naught Ni by 2 into sin theta 1 plus sin theta 2. If the solenoid is infinitely long, then theta 1 will be, to join on this side, you will have to go up to infinity. Theta 1 will be 90. And to join on the other side, you will have to go up to infinity. Theta 2 will also be 90. So if the solenoid is infinitely long, then both theta 1 as well as theta 2 is 90 and 90. Sin 90 is 1. Sin 90 is 1. Sin 90 plus sin 90 becomes 2. So you get magnetic field will be mu naught Ni. So if you have got an infinitely long solenoid, then the magnetic field at a point inside the infinitely long solenoid is nothing but mu naught Ni. Remember that the magnetic field inside a long solenoid is nearly uniform and the magnetic field outside is 0. Magnetic field inside a long solenoid is nearly uniform, and magnetic field outside the solenoid will be 0, mu naught Ni. Next thing, bachcho, focus. If rather than having a solenoid, you have a toroid, you take a flexible tube, wind a wire on top of it. This is a solenoid. Join the two ends. Now what you have got is a toroid. On the toroid, if you wind a wire and you drive some current into it, the difference between the solenoid and the toroid is that when you drive a current in a solenoid, magnetic field lines are inside the solenoid, but they do also come outside the solenoid. So solenoid produces magnetic field lines both inside it as well as outside it. Remember this, we say that the magnetic field produced by solenoid outside is negligible, very small, but it exists. So magnetic field produced by solenoid, inside it is nearly uniform, outside it is negligible. Magnetic field produced by solenoid, inside it is nearly uniform, outside it is negligible. For a toroid, all the magnetic field lines created by toroid is found within the flexitube. All the magnetic field lines created by toroid are within the tube. So beta, first of all, let's mug up three things. First, formula of toroid. So if you have got n turns here, and let's say this toroid has got inner radius R1 and outer radius R2. Same formula. Magnetic field inside the toroid is mu naught Ni. What is N? Number of turns per unit length. How do you write here? Number of turns on the toroid upon mean perimeter. What is mean perimeter, betu? Mean perimeter means average perimeter. Inner perimeter plus outer perimeter by 2. Inner perimeter will be 2 pi R1. Outer perimeter will be 2 pi R2. Inner perimeter plus outer perimeter by 2. This is called mean perimeter. So magnetic field inside the toroid is N upon 2 pi R1 plus 2 pi R2 by 2, which is pi times of R1 plus R2. Fair enough, betu? Now, magnetic field within the tube is mu naught Ni. Number of turns per unit length has to be taken as number of turn upon mean perimeter. Two important thing. Important thing, number one. Field created by, magnetic field created by toroid is found within its tube. Is found within its tube. So field lines do not escape the tube of the toroid. In case of solenoid, you find even the field lines outside the tube. Second point which get asked. Magnetic moment of a solenoid is non-zero, while the magnetic moment of a toroid is 0. Magnetic moment of a solenoid is non-zero. In solenoid, you have got multiple turns. Okay. The magnetic moment associated with each turn is in same direction. You have got multiple turns. How do you get bhai sahab direction of magnetic moment? If let's say current is clockwise, magnetic moment inward. Current is anti-clockwise, magnetic moment outward. So if you have got a solenoid, every single turn carry current in same sense. So direction of magnetic moment towards right. For toroid, it is wounded over a flexitube. So direction of magnetic moment keeps on changing direction. So when you think of all the vectors due to each magnetic moment in case of toroid, they will be aligned head to tail on a circle and their net resultant is 0. Chupchap mug up. Magnetic moment of solenoid is non-zero. All the magnetic moment vector are in straight line. Magnetic moment of toroid is 0 because all the magnetic moment align on a circle. Mug this up. Chal beto. With this thing done, 3-4 important thing. If you have got two parallel current carrying wire, carrying current I1 and I2 separated by distance d, if they carry current in same direction, they will attract repel. If they carry current in same direction, they will attract repel. So if they carry current in same direction, they will attract. And if two current carrying wire carry current in opposite direction, then they will repel. So two current carrying wire carrying current in same direction attract. Two current carrying wire carrying current in opposite direction will repel each other. This get asked a lot. What is the force acting per unit length between two current carrying wire separated by distance d? What is the force acting per unit length between two current carrying wires separated by distance p? So you will say, at position of second current carrying wire, the first current carrying wire produces a magnetic field. How much? Mu naught I1 by 2 pi t. The force acting on the second current carrying wire I2 due to the magnetic field produced by the first current carrying wire at position of second current carrying wire will be given by this. Think of a length L of second wire. The force acting is given by I, current in the second wire, into length of second wire times magnetic field produced by first wire at position of second wire. So the force acting per unit length will be nothing but mu naught I1 I2 by 2 pi d. So this is the force acting per unit length due to the magnetic field produced by first wire at position of second wire. This is important. Chalo bachcho. Now we have got 18 minutes left. I am jumping the whole topic of EMI and I am going to AC because as much as I roam around in kids, I think that AC require more help than EMI. So I am talking more of AC now and not of EMI. Magnetism and matter, beta, very theoretical topic. Magnetism and matter. Please read here para, dia, ferro. Kids are always running away from reading. Beta, para, dia, ferro material solving will take you as much time as it takes you to solve inorganic chemistry material. It's theoretical. Now. If it is so, it is so. Nothing to think. Get the para, dia, ferro done. In geomagnetism, if that's a headache, I recommend you mug up only 3 things. First of all, what is the definition of angle of dip? The angle made by the Earth's magnetic field with the horizontal. Read it till the time you understand it. The angle made by Earth's magnetic field with the horizontal. Then mug up what is the angle of declination. Read the definition 5 times. The angle made by horizontal component of Earth magnetic field with the true north. The angle made by horizontal component of Earth magnetic field with the true north. And once you are done with this, mug up a ghatiya sa formula. Tan of the apparent angle of dip equals to tan of the actual angle of dip upon cos theta, where theta is the angle made by the vertical plane of dip circle with the magnetic meridian. So these 3 things, get it done in Earth's magnetism also. Rest better that bar magnet, that thing is easy. When you cut a bar magnet this way, what happens? This way, what happens? Revise that. Magnetism and matter, revise on your own. Let's move on to AC B2. First thing, let's talk about pure circuits. 2, 3, simple thing. What is the average value of sine omega t over 1 complete cycle? What is the average value of sine omega t over 1 complete cycle? So you'll say, but sine omega t graph goes like this. Half the cycle sine omega t is positive. Half the cycle sine omega t is negative. Average value of sine omega t over 1 complete cycle is 0. Next question. What is the value of cos omega t? What is the average value of cos omega t over 1 complete cycle? What is the average value of cos omega t over 1 complete cycle? What is the average value of cos omega t over 1 complete cycle? So you'll say, but cos omega t versus t graph goes something like this. This is 1 complete cycle. Here, cos omega t positive, negative, negative, positive, positive, negative, negative, positive. What is the average value of cos omega t over 1 complete cycle? 0. So average value of sin omega t and average value of cos omega t over 1 complete cycle is 0. Next question. What is the average value of sin square omega t over 1 complete cycle? What is the average value of sin square omega t over 1 complete cycle? So it's the average value of sin square omega t. Sin square omega t. Sin square omega t can never be negative. So it changes bit from 0 to 1 to 0 to 1 to 0 to 1. The average value of sin square omega t over 1 complete cycle is half. Minimum value of sin square omega t is 0. Maximum value of sin square omega t is 1. Sin square omega t oscillate between 0, 1, 0, 1, 0, 1, 0, 1. So what is the average value of sin square omega t over 1 complete cycle? Half. Similarly, what is the average value of cos square omega t over 1 complete cycle? Again, half. Beto, maga, Average value of sin omega t. So sin omega t, half cycle positive, half cycle negative, 0. Cos omega t, half cycle positive, half cycle negative, 0. Sin square omega t. Sin square omega t is never negative, sin square. So it changes from 0 to 1 to 0 to 1 to 0 to 1. Average value of sin square omega t over one complete cycle is half. Average value of cos square omega t, again it can never be negative, is half. Marked up? Chal betu. Question get asked. Current in a wire is given as A plus B sin omega t. What is the average value of current? What is the RMS value of current? What is the average value of current? What is the RMS value of current? So you'll say, fuck, average value of current, average value of current, average value of A. What is the average value of a constant? If I tell you a girl gets 95 marks in every single physics test, what is her average marks in physics? You'll say 95. Bhai, the average value of a constant is same thing. So you will say average current equals to average value of A plus average value of B sin omega t. Average value of A is A. Average value of B sin omega t. Average value of sin omega t over one complete cycle is 0. So you will say average current is A. Okay, betu? If I ask you what is IRMS, so you will say, okay, you are asking me IRMS. So sir, square it, then mean it, then root it. Square it, mean it, root it. Square it, mean it, root it. So first I need to square this function. So I will say I square equals to A square plus B square sin square omega t plus 2AB sin omega t. Square it. Then we have to find its mean value. Mean value of I square is mean value of A square, which is A square. Mean value of B square sin square omega t, how much? B square sin square omega t. Mean value of sin square omega t is half. What is the mean value of sin omega t? 0. So IRMS is square it, then find the mean value, then take the root. This is IRMS. Square it, mean it, root it. So you get under root of A square plus B square by 2. So the first thing to mug up in AC is average value of sin omega t and cos omega t over one complete cycle is 0. Average value of sin square omega t and cos square omega t over one complete cycle is half. When they say IRMS, it means that square it, then mean it, then root it. Square it, then mean it, then root it. Okay. If I give you current flowing in the line is A sin omega t plus B cos omega t. First question, what is the average value of current? You'll say average value of current, average value of A sin omega t is 0. Average value of B cos omega t is 0. 0 plus 0, 0. Then, if I ask you what is IRMS, you'll say, IRMS. So step 1, square it. When you square it, Gudda, you get A square sin square omega t plus B square cos square omega t plus 2AB sin omega t cos omega t. Squared it, now mean it. When you take the mean value of sin square omega t is half, mean value of cos square omega t is half. Beta, this 2 sin omega t cos omega t can be thought of as AB sin 2 omega t. And on taking the average value of sin t is 0. So you get plus 0. So IRMS, root mean square. So IRMS will be under root of A square plus B square by root. Fair enough? But to next thing, we need to talk about is phasor. I will extend this lecture by 15 minutes or maybe 20 because these things are important, which I'm doing right now. Okay, but focus here. To use the phasor method, first thing we need to understand is how to compare the phase. To compare the phase, use this simple rule. Whenever they write sin theta, then beto sin theta is sin theta. Okay. Whenever they write cos theta, think of cos theta of sine of theta plus 90. Sir, we can even think of cos theta as sine of 90 minus theta. Na? Yes, you can think. No problem there. But it's better to think this way. Sin theta is sin theta, cos theta is sine of theta plus pi by 2. Minus sin theta is sine of theta plus pi. Minus cos theta is sine of theta plus 3 pi by 2. So, beta maga sin theta is sin theta, cos theta is sine of theta plus 90, minus sin theta is sine of theta plus pi, yes. Minus cos theta is sine of theta plus 3 pi by 2. There is a pattern. Sine, cos, minus sine, minus cos. Sine, cos, minus sine, minus cos, 0, pi by 2, pi, 3 pi by 2, 0, pi by 2, pi, 3 pi by 2. So if you mark them, all of them together, then it helps in easier phase comparison. If I ask you simple question from SHM, x equals to a sin omega t and y equals to b cos omega t. What is the phase difference between these two SHMs? So you'll say, dekho sir, to compare the phase differences, step 1, make the trigonometric function same. So having one as sine and one as cos, you can't compare the phase. Make the trigonometric function same. Sir, how to make it same? Abhe, just learn na. Sine is sine, cos is sine of theta plus pi by 2, minus sine is cos sine of theta plus pi, minus cos is sine of theta plus 3 pi by 2. So first of all, make the trigonometric function same. Think of it as b sine omega t plus pi by 2. So for first one, you will say trigonometric function is sine and phase angle is omega t. For second one also, now trigonometric function is sine and phase angle is omega t plus pi by 2. So what is the phase difference? Omega t plus pi by 2 minus omega t, which is nothing but pi by 2. Now beta, there is something called phasor method. Phasor method. So what the hell is a phasor method? Phasor method is a method used to add up multiple sinusoidal function. Phasor method is a method used to measure multiple sinusoidal function. It's kind of like a trick. Here we treat every signal or every oscillation as a vector. Every oscillation as a vector. To define a vector, you need two things. What? Magnitude and direction. So amplitude taken as magnitude. Amplitude taken as magnitude. And phase angle taken as direction. Need to listen. Amplitude is taken as magnitude and phase angle is taken as direction. For example, they will say the position of a particle is given by 6 sin omega t plus 8 cos omega t. What is the amplitude of oscillation of particle? Phasor method is a method used to add up multiple sinusoidal functions. When you add them using the phasor method, you treat every single sinusoidal function as a vector. To define a vector, you need two things: magnitude, direction. Magnitude is same as the amplitude. For first vector, magnitude is 6. For second vector, magnitude is 8. The direction is taken same as the phase angle. But before you do anything, better make sure that both are same trigonometric function. How to do? Abhe, first thing learn. Whenever they give sin theta, it's sin theta. Whenever they give cos theta, it is sin of theta plus pi by 2. Whenever they give minus sin theta, it is sin of theta plus pi. Whenever they give minus cos theta, it's sin of theta plus 3 pi by 2. So here you will write x equals to 6 sin omega t plus 8 sin omega t plus pi by 2. Okay? Now treat the first one as a vector of magnitude 6 in direction of omega t. So what is the meaning of direction of omega t? Beta, you can choose any random direction as omega t. So I am choosing this direction towards right as omega t. So in this direction, think of a vector of magnitude 6 in direction of omega t. Now think of another vector of magnitude 8 in direction of omega t plus pi by 2. I know that you know that the resultant of these two vectors of 6 and 8 will be 10. The angle opposite to 8 will be 53 degree. So the resultant of these two vectors is a single vector of magnitude 10, making an angle of 53 degree with the omega t. So the phase of the resultant is omega t plus 53 and the amplitude of resultant is 10. So you will say that this two are same as 10 sin omega t plus 53 degree. Sir, from the top quickly, what are we doing? We are adding up multiple vibrations, multiple sinusoidal function. How? Using the phasor method. What is phasor method? In phasor method, we treat every single sinusoidal function as a vector, having magnitude same as amplitude, having direction same as phase angle. Whenever you do phase comparison, beta, make sure that you make the trigonometric function same first. So for example, darling, if you get this question, x is 6 sin omega t plus 6 root 3 cos omega t. Okay. Now, what is the resultant equation? You will say, देखो sir, पकाओ मत बिल्कुल. This is sin omega t. Here I will think of the second one in the sine function as sin omega t plus pi by 2. So first vector is a vector of magnitude 6 in direction of omega t. Second vector is a vector of magnitude 6 root 3 in direction of omega t plus pi by 2. The resultant of this 6 and 6 root 3 will be under root of 6 square plus 6 root 3 square. Beta 6 square is 36 and 6 root 3 square will be 36 into 3. So when you calculate it, it will come out to be 12. Do the maths. What will be this angle theta? You will say tan theta will be 6 root 3 by 6. So tan theta will be 6 root 3 by 6, which is root 3. So theta will be nothing but 60 degrees. So you will say that the resultant of these two is nothing but 12 sine omega t plus 60 degrees. Okay, this is how we use the phasor method. Good. Now better focus here. Before we go anywhere further, first we need to understand something called pure circuits. Pure circuit means when you connect a resistor with an AC, what happens? So let's say you have an AC of voltage V0 sin omega t and you connect it with a resistor. You know there is something called Ohm's law. The potential drop across the resistor equals to current times resistance. Here the potential drop between these 2 points at any instant is V0 sin omega t. So you'll write V0 sin omega t equals to I into R. So current in the flowing in the line is nothing but V0 by R sin omega t. Current flowing in the line at any instant is V0 by R sin omega t. If I ask you what is the maximum value of current flowing in the line, you will say the maximum value of current flowing in the line is nothing but V0 by R. Second thing, if I ask you, what is the phase difference between potential drop across the resistor and current flowing through the resistor? So you will say, dekho sir, trigonometric function is same sin as well as the input is same omega t. Hence the phase difference between the current and potential drop is 0. Okay, but next question. If we increase the omega of the oscillator or decrease the omega of the oscillator, will the peak current flowing through the resistor change? You will say, dekho sir, peak current flowing through this resistor is peak potential drop divided by R. So whether you increase omega or decrease omega, the peak current flowing through the line won't change. The peak current flowing through the line won't change. So this is case number 1. Here, two things have to be marked up. In case of pure resistive circuit, peak current is peak potential drop upon resistance, and there is no phase difference between current and potential drop. Second way 2, pure capacitive circuit. Mark up one of them, capacitive or inductive, other one will be easy. Let's say you have got this capacitor of capacitance C, and across this you have connected a AC voltage V0 sin omega t. So this potential keeps on changing with time. For the capacitance, the basic equation equals to Q equals to C delta V. Now here the potential drop across the capacitor changes with time as V0 sin omega t. So the charge on the plate of capacitor at any time t is C V0 sin omega t. C V0 sin omega t. Current flowing through the capacitor will be dq by dt. So once you differentiate it, you get C V0, differentiation of sin omega t is cos omega t multiplied by omega. So I comes out to be C V0 omega cos omega t. If somebody asks you, bhai sahab, what is the current flowing through the current capacitor at any instant, you will say C V0 omega cos omega t. If now they ask you what is the peak value of current flowing through the capacitor, you will say peak value of current flowing through the capacitor is C V0 omega. Now they go. Physicists love to correlate things. We already know Ohm's law. Peak current equals to peak potential drop by resistance. Here also we want something same. Peak current flowing through the capacitor equals to peak potential drop by something. But it's not by something, it's into something. So you can think of this as peak current equals to peak potential drop by 1 by omega c. And then we call this quantity 1 by omega c as capacitive reactance. So you say that the peak current in the line is peak potential drop across the line upon omega c, which is xc. So remember that capacitive reactance is 1 by omega c. Capacitive reactance is 1 by omega c. When you increase the omega, If omega becomes double, capacitive reactance becomes how many times? Sir, if omega becomes double, capacitive reactance becomes half. If capacitive reactance becomes half, the peak current flowing in the line becomes how many times? Sir, capacitive reactance is kind of like resistance, but for capacitor connected in AC. So if you are saying omega becomes double, XC becomes half. If XC becomes half, denominator becomes half. The peak current will become double. Or you can see directly. If omega becomes double, the peak current will become double. Next thing. What is the phase difference between potential drop and current here? So here you will say that current can be written as I naught cos omega t, and cos omega t can be written as sin omega t plus pi by 2. So there is a phase difference of pi by 2 between current and potential. Here current leads potential. Here current leads potential. In which one? In pure capacitive. So in pure resistive, peak current is peak potential drop by R. Phase difference between current and potential is 0. Both are in same phase. In pure capacitive circuit, peak current equals to peak potential drop by XC, where XC is 1 by omega C. Here current leads potential by phase of pi by 2. Current leads potential by a phase of pi by 2. Similarly, in a pure inductive circuit, the peak current is peak potential drop by XL. Here XC is 1 by omega C. So as omega increases, XC will decrease. Here we say XL is omega L. So as omega increases, inductive reactance increases. And here potential leads current by a phase of pi by 2. Beta, what is inductance? Sir, inductance is the property of a substance by the virtue of which it opposes the change in current. Inductance opposes change in current. So inductor doesn't allow the current to change. So when the potential changes, it takes some time for current to change. That's why in pure inductive circuit, current lags. Sir, I didn't get it. Listen once more. Inductance is the property of a substance by the virtue of which it opposes change in current. Inductor opposes change in current, right? When you connect an AC, potential changes quickly. Inductor doesn't like that the current should change quickly. So it opposes the change. That's why in pure inductive circuit, current lags. In pure capacitive circuit, current leads. In pure resistive circuit, current and potential drop are in same phase. Then we have got something called series LCR circuit. In a series LCR circuit, you connect C, L, R on in series across an AC. Okay. Now better focus. Few important things. We define something called impedance for a series LCR circuit. The impedance of a series LCR circuit is under root of R square plus XL minus XC whole square. Under root of R square plus XL minus XC whole square. Beta, what is XL? What is XL? Omega L. What is XC? 1 by omega C. Remember that the peak current flowing in the series LCR circuit is peak potential drop upon impedance of circuit. Peak current flowing equals to peak potential drop upon impedance of the circuit. If in a particular circuit, let's say this is the phase of current, the potential drop across the resistor is in same phase as the current. The potential drop across the inductor leads the current by a phase of pi by 2, and the potential drop across the capacitor lags by a phase of pi by 2. The resultant of these three vectors, XL, R and XC, this is called something like impedance triangle. So this value is what? Resistance. This value is what? Reactance. This is resistance of the line. This is reactance of the line. And their resultant is called impedance of the line. Impedance of line is under root of R square plus XL minus XC whole square. Impedance of line is under root of R square plus XL minus XC whole square. Beta, this angle theta, na, represents the phase difference between potential and current. This angle theta represents the phase difference between current and potential. Now, if I ask you what is tan theta, you will say tan theta is reactance of line upon resistance of line. If I ask you what is cos theta, you will say cos theta is resistance of line upon impedance of line. If I ask you what is sin theta, you will say sin theta is reactance of line minus impedance of line. So cos theta is R by Z. This is important. This is called power factor. If you have got a circuit in which current flowing is I naught sin omega t and potential drop across the circuit is V naught sin omega t plus phi. If I ask you what is the phase difference between the current, GeoNet issue happening, sir, can you put this app or at least QR code provide? Okay. Current is I naught sin omega t, potential is V naught sin omega t plus phi. Question is, what is the average power dissipated? We say that average power dissipated is Vrms, Irms, cos phi. Here cos phi is nothing but power factor, which is R by Z. Irms is peak current by root 2. Vrms is peak potential drop by root 2. So this is the average power dissipated in series LCR circuit. Now better focus 2-3 more thing. Resonance condition. When do you say that series LCR circuit is under resonance condition? When impedance of the circuit is minimum. Impedance is minimum equals to R. When XL minus XC becomes 0. XL minus XC becomes 0 means XL equals to XC. XL is omega L, so omega L equals to 1 by omega C, so omega equals to 1 by root LC. So under resonance condition, angular frequency has to be 1 by root LC. Under resonance condition, impedance is minimum equals to R. Under resonance condition, what is the power factor? Power factor cos theta is R by Z. Under resonance condition, since Z is equals to R, power factor is 1. Remember that under resonance condition, power factor is 1. Okay, and under resonance condition, no phase difference between current and potential drop across the line. No phase difference between current and potential drop across the line. Okay, bachcho, these are important points which have to be mugged up for resonance condition. Next thing, there is something called quality factor. Sir, what to mug up in quality factor? 3-4 things we do. The formula of quality factor is 1 by R under root L by C. Quality factor is 1 by R under root L by C. Quality factor can also be written as resonance frequency upon bandwidth. Resonance frequency upon bandwidth. If you plot the maximum current flowing in LCR circuit versus omega, there is one particular omega for which current flowing in the line is maximum. That omega is resonance frequency. Think of two another omega nearby the resonance frequency. Let's call it them omega 1 and omega 2. These omega 1 and omega 2 are called half power frequencies. The frequencies at which the power dissipated in the circuit is half the maximum, half power frequency. Let's say the gap between these two half power frequency is delta omega. This delta omega is called the bandwidth. So what is delta omega? It is bandwidth. That is gap between the two half power frequencies. Half power frequency. That is the gap between the two half power frequencies. Now beta, let's move on to something called LC oscillation. Before we go to LC oscillation, you should know this comparison table between the mechanical system and the electric system. Mechanical system and electric system comparison. I know you are tired. 5 more minutes. This is important. Something can come from this particular thing. So comparison between mechanical system and electrical system. Have you ever wondered why do they call E electromotive force? Electromotive force actually is work done per unit charge. Still they call it electromotive force because initially they were comparing electrical system to the mechanical system. In mechanical system, we have got something called displacement. The analogous to electrical system is charge. The rate of change of position is called velocity. The rate of flow of charge is called current. So what is velocity here? There you have got current. In mechanical system, you have got something called mass, which represents the amount of inertia. The more the mass, the more the inertia, the more it opposes the change in velocity. In electrical system, we have got something called inductance. The more the inductance, the more it opposes the change in current. Here we have learned something called acceleration, which is nothing but dv by dt. Here the equivalent of acceleration is velocity is equivalent of current. Velocity same as current. Position same as charge. So acceleration is dv by dt. Here the equivalent of acceleration is nothing but di by dt. Here we write mechanical equation. F equals to ma. Force equals to mass into acceleration. Its equivalent here, EMF, equals to minus L di by dt. So beta, that's why they started calling EMF just like force, electromotive force. Electromotive force is not a force. It is the work done per unit charge. F, force, equals to mass, inertia times acceleration. Here E, L di by dt. Betu, keep focusing. Tell me, keep on correlating. Tell me, here you have got force. There you have got what? EMF or potential drop. है ना? EMF or potential drop. You use both the term invariably. Chalo betu, tell me. We know that momentum is mass times velocity. Which quantity is equivalent to momentum in the electrical system? Which quantity is equivalent to momentum in the electrical system? So, sir, in place of mass, you should write inductance. Huh? In place of velocity, you should write current. Huh? Phi equals to Li. So, here you write beta P equals to mv. There, phi equals to Li. Flux is equivalent of momentum in the electrical system. Here you write beta kinetic energy equals to half mv square. Which formula is equivalent of this in the electrical system? So in place of mass, inductance, in place of velocity, current. So here you write na energy stored inside the inductor half Li square. Here beta you can even write kinetic energy as P square by 2m. What is the equivalent equation of this in the electrical system? So sir, in place of momentum you can write phi. So phi square by 2. In place of mass you can write L. Phi square by 2L. Okay. Next betu. In the electrical system, electrical system you have something called, in the mechanical system you have F equals to Kx. Force is same as EMF or potential drop. Position is same as charge. Potential drop and charge equation there. Q equals to C delta V. Now beta dekh, order is different. F equals to Kx. Here Q equals to C delta V. Think of it as delta V equals to Q by C. So what you have as a spring constant in the electrical system, same thing you have as 1 by capacitance in the electrical system. So spring constant in mechanical, 1 by capacitance in electrical. Next, here you write energy stored inside the spring is half Kx square. There you write energy stored inside the capacitor as Q square by 2C. They were to compare. Spring constant is same as 1 by C. So what am I doing? I am quickly correlating the electrical and mechanical system. Mechanical system charge, mechanical system X, electrical system charge, mechanical system velocity, electrical system current, mechanical system mass, here inductance, their acceleration, here di by dt, their force, here electromotive force. There P equals to mv, here phi equals to Li, half mv square, half Li square, F equals to Kx, and here you write delta V equals to Q by C, their spring constant, here 1 by C. Done? Number 2 thing. All the LC oscillation questions can be done using again all the SHM equation. Wait to tell me, in mechanical system, how do you write angular frequency of SHM? So angular frequency under root of angular frequency, how do you write? Omega equals to root m by k, है ना? Or root k by m. What should I write? Nobody is answering. Everyone is sleeping now. Shant. Betu, mechanical system. Omega is what, Betu? Root m by k, root k by m. Okay, focus here. F equals to minus kx, Betu. Ma equals to minus kx. So m into d square x upon dt square equals to minus kx. Okay, this is the equation in mechanical system. In electrical system, we write same thing as potential drop across the inductor minus L di by dt equals to potential drop across capital Q by C. In place of I, you can write dq by dt. So I d of dq by dt equals to Q by C. So here you get d square q upon dt square equals to minus q by cl. Okay, beta. Here you write d square x upon dt square as minus k by m into x. Here you say this thing is omega square. Omega square is k by m. Here you say 1 by this thing is omega square. So omega square is 1 by LC. So here you get omega as 1 by root LC. Here you get omega as under root of k by m. Omega is under root of k by m. So better focus here. Mechanical. Last thing. Electrical. Better focus. Here omega is under root of k by m. What is same as mass in the electrical system? Same as mass. Inductance, same as spring constant, 1 by C. So 1 by C into L. So 1 by LC. Okay, this is omega. Here better time period 2 pi under root m by k. Here time period, in place of m you will get L, and in place of 1 by k, C. Okay, here focus next. The most important equation in entire SHM, 3-4 things, better important first. When a particle performs SHM, maximum velocity at mean position. Maximum velocity at mean position is omega times A. What is A? A is maximum displacement. Same thing you can write here also. The maximum current flowing through the inductor in LC oscillation, here velocity, there current, equals to omega times, which is 1 by root LC, time maximum displacement here, their maximum charge. So the maximum current flowing through the inductor and maximum charge on the plate of capacitor in LC oscillation are correlated as I max equals to 1 by root LC Q max. Here we to next thing. Here you say the velocity of a particle doing SHM at any instant is omega under root of A square minus X square. In LC oscillation, you say that the current flowing in the circuit at any instant equals to omega under root maximum charge on the plate of capacitor whole square minus the charge on the plate of capacitor at that instant whole square. I equals to omega under root of Q naught square minus Q square. So these are some correlations which you should know between LC means electrical and mechanical system. Revise your notes once, go through them quickly. Any question which is bigger than this solution, no need to read it, whether in gym, whether in notes, anywhere. Now you need to revise only small thing. See you guys. Tata, bye bye, all the best. Keep working hard.